Good afternoon, everybody. It's our pleasure to invite all of you to this session on foundations of AI and ML. What we have planned is two sessions today, one today and one tomorrow. Today's session will be largely foundational questions in machine learning. And machine learning, as we know, today is very different from what it was 10 years ago. Technology, of course, contributing to a large extent to its applicability. We are also at a very exciting point in time where you have people from different disciplines, biologists, neurologists, doctors, lawyers, administrators, all making attempts to talk a language which was once very exclusively the domain of a community of researchers doing AI, some of whom you will actually be hearing on this in these 2 days. Now we seek, people are seeking collaborations and trying to find new novel ways to leverage AI for use in society. So it's really exciting that way. But it's also a very exciting time for theoreticians, not necessarily only people who actually implement systems. Even for theoreticians, what the current models have actually thrown up are extremely interesting questions, and it is not very clear whether the classical framework of learning theory would be able to answer these questions. So, of course, the topmost among them being the remarkable generalization that these highly over-parameterized neural networks seem to achieve. It's still a mystery. There is very exciting work going on in trying to explain that. The other thing, of course, is the remarkable success of the stochastic gradient descent algorithms on problems which are very, very non-convex. What exactly is being learned? What are the representations that these models are learning? These are all very interesting questions from a theoretician's point of view. And of course, this will feed off into practice or positively. Today we have a group of very distinguished speakers, if I may say, who have contributed of course, to the spectacular progress that we see in their own unique ways. They have all been responsible for sort of pushing the boundary of what we understand. Yeah, I'm sure you will be in for some really good talks. So without much ado, I will invite the first speaker. Yeah. So the first speaker is Hariharan Narayanan. So he is currently at the Tata Institute of Fundamental Research. So Hariharan will talk us through fitting a manifold of large reach to noisy data. So Hari is sort of an expert in this area, and he has done some really foundational work, I think. Yeah, Hari.
Thank you very much. So shall I share my screen?
Yeah, I think one of them will allow you to do it. Sujit should allow you. Or can I do it? I can also do it probably. Sorry, then I can do it. Yeah.
Sorry.
Yeah, there you are. Yeah.
So thank you very much for the invitation to speak here. I'm going to be talking on fitting a manifold of large reach to noisy data. This is joint work with Charles Pfefferman, Sergey Ivanov, and Marty Lasser. So the manifold learning is based on what is generally called the manifold hypothesis, which is that high-dimensional data can be modeled to lie in the vicinity of a low-dimensional manifold. This is, of course, not always true, but in the cases where it is true, we expect that the methods coming from manifold learning should be helpful. So what I've shown here is a picture of a torus, which is a manifold, the surface of a donut, and some points that appear to lie rather close to the surface. So more generally, why should measurements lie near a manifold? What are the settings where this should happen? So generally, these happen if the data is generated by some process which inherently has symmetries or other reasons for it to be locally low dimensional. So here is one concrete example, that of cryo-electron microscopy. Here a beam of electrons is fired at a frozen protein solution, and the emerging scattered electrons pass through a lens to create a magnified image on a detector from which the structure can be worked out. So generally this is done for large biological molecules like viruses. And what you see on the screen is a two-dimensional image. It's not a shadow in the usual sense. It is rather what happens when an electron beam passes through the virus, for example, and what you see at a given point is an attenuation of the electron beam that is proportional to the line integral in that particular direction when the electron beam passes through the virus. So it's a kind of shadow, but it's just that the electron beams go all the way through. So and what we are collecting is several such photographs from a column as the virus rotates. Now the action of the rotation is the same as the action of SO3 on the virus. So there is a correspondence between the images and the group SO3. Once you, for example, fix the initial orientation for the virus. So in this way, we expect that the cryo-electron images lie on some sort of image of SO3 under some complicated map. Now, these things are going to be pixelated and viewed in some high-dimensional space and so on. So while SO3 is three-dimensional, this set of images, in each individual image is an element in, let's say, 40,000 dimensions, if it's a 200 by 200 image, as I will show in the next slide. Then we expect to have something like a three-dimensional submanifold of 40,000 dimensions. So here are, for example, two actual images that are obtained in a biological lab, and these are 40,000 dimensional images with 200 by 200 pixels. And I mean, one would imagine that if the symmetries are if the process of going from SO3 to the image is somehow doesn't lose the topology, then you expect that you would see a image that is again let's say homeomorphic to SO3. So here I'm explaining this again, a 40,000 dimensional image, and assuming the noise is small, the points. So again, this is a very noisy process, and the points are not going to be on this, let's say, manifold, but it'll be close to it, or if you're lucky, or actually quite far from it if the noise is large. Noise is actually large in cryo-EM. So what I'm saying not quite applicable, but if there's a corresponding situation where the noise is small, then these points approximately lie in an orbit of SO3 with three-dimensional Lie group. And assuming the molecule is generic, meaning it doesn't have, for example, have icosahedral symmetries, which viruses often do, the orbit would be a three-dimensional manifold diffeomorphic to SO3. So here is another example where data is lying on a immersed Klein bottle with additive Gaussian noise. So now I'm going to go into the theoretical underpinning. So here, I want to define a manifold learning problem in theoretical terms and then give an algorithm that solves this problem. So I'll have to now describe what I mean by a manifold in quantitative terms. So for us, a manifold will be a d-dimensional submanifold which has no boundary. So not manifolds with boundary, rather just manifolds, and is C2, meaning it is locally twice continuously differentiable. So the graph of this manifold locally is a twice continuously differentiable function. And the reach of the manifold is at least tau, by which we mean that there is a tube, one can construct a tube of radius at least tau that does not self-intersect as it goes over the manifold. And also the d-dimensional Hausdorff measure is at most V. It's simply the volume is at most V. So M has no boundary, d-dimensional C2 means that what I just said, if you take a disk and you view the graph, the function from a d-dimensional disk to the normal space, then the graph of this function is twice continuously differentiable. And here are some pictures. So here is a curve of large reach. Here is a curve of small reach. It's roughly speaking the radius of the oscillating circle in this case. So you have these oscillating circles which match the curve both in derivative and second derivative. So that's why it looks like it's really touching the curve here. And that's called an oscillating circle. And in this case, the radius of this oscillating circle, minimum radius that it has is the reach. And Hausdorff measure, this is defining how to define the volume in general using tubes. But I think I'll skip this more or less. So now this is the generator model. There is this manifold which we don't know. X1, X2, Xn are IID draws from a measure, the logarithm of whose Radon-Nikodym derivative with respect to the d-dimensional Hausdorff measure is C Lipschitz. So what this is just saying is that the density never becomes too small and the density is Lipschitz, meaning if you take two nearby points, the change in the density is at most some constant C times the distance between those 2 points.
Mm-hmm.
Next, these points are sampled from the manifold, and then you have Gaussians added, independent Gaussians added to these points. These independent Gaussians have standard deviation sigma in each direction, which means that typically they are going to be root n times sigma from the origin. So that's what happens. If you have an n-dimensional Gaussian in each direction, the standard deviation sigma, a typical point is square root n times sigma from the origin. But these are very big, very large deviations, although the noise in each direction is small. And we're going to assume that tau is by some small factor is greater than sigma square root d. So this capital D is not n, it is much smaller than n. It comes from a dimension reduction step that happens via PCA or principal component analysis. The results of this talk guarantee for sufficiently small sigma a Hausdorff distance of order sigma squared with less than order sigma to the minus 2d plus 4 samples. So what this means is that we are going to actually produce a description of a manifold that is very close to the original manifold. And further, even the reach is not too bad. Small reach is bad than big reach. And this reach is degrading by only d to the 6th rather than some exponential factor in d, which is what happens if one is not particularly careful about this factor. So this first step is principal component analysis. So you project, you first do a principal component analysis with sufficiently many dimensions. You project onto this subspace, and this brings down the ambient dimension from n to d. The value of d only depends on intrinsic parameters d, tau, and v. Let x be a finite set of points in E with so this R to the D is, we are not presupposing that we have already projected all the points onto the PCA subspace, and now we are working there. And the point is that if this PCA subspace has sufficiently large dimension, it will end up being rather close to every point of the manifold. And so when you project the true manifold onto this PCA subspace, what will happen is that the distortion incurred on the manifold will be very small because it's moving very little. And the manifold also has a reach bound. So when you have a manifold with a lower bound on the reach, if you project it onto a subspace that's very close to it, it not only does it incur very little metric distortion, the reach of the image is also quite large compared to the original. So it's in every way satisfactory. We don't really mind. And you've also reduced the dimension dramatically. Okay, so then, so let X be a set of points in this reduced subspace. And now we have to, yeah. Is there a question?
I don't think so.
No, I don't think so. Just continue, Hari, sorry. There was just a mic problem.
Yeah. So, so we are now going to be fitting a manifold in this subspace to the data. And the way it's going to be done is we'll first fit a family of disks of certain of a certain radius. In this case, I think the disks are let's say of so the disks are disks are at radius disks are of radius 1, and we are given a guarantee that the Hausdorff distance to the disks is less than delta. So here is a sub problem now. There is a set of points. We have to find a unit disk such that the Hausdorff distance to the of that point cloud to this. By Hausdorff distance, what do we mean? It's simply the maximum distance of any point in that point cloud to the disk. That has to be less than c d delta. The guarantee is that there actually is a disk whose Hausdorff distance is less than delta, which we don't know. So this is the unknown. What we have to find is a reasonably good surrogate for that disk whose Hausdorff distance is less than c d delta. And this is how we go about doing that. The basic idea is to choose an orthonormal basis of d vectors from the point cloud itself, and just take the span of that and take the ball using that span. Okay, so why does this work? It uses some matrix analysis actually, and I can't go through that here. But basically, this is the algorithm. Like this is spelled out. But it's just what I just said. You keep picking unit vectors that are orthogonal to all the preceding unit vectors from the point cloud. They will not be exactly orthogonal, but if you have enough points, you will be able to choose a point that is roughly orthogonal to the preceding ones. And you keep doing this, and at the end of the day, so note that these points, you can draw a lot of points. You're allowed to draw a lot of points. So there's no dearth of points. And now this d-dimensional disk is actually the dimension of the manifold. So d is very small. Think of d equal to 3, for example, in the cryo-EM example. So you can afford to have exponential in d points. It's not going to be very huge. And that is the setting where we are working. And then we just need to pick this good disk. But we have to do this again and again. So we pick this disk, and then this disk does satisfy CD delta Hausdorff distance. And once we do that, we pick a number of disks so that firstly, the Hausdorff distance condition is met. Secondly, the centers of these disks are sufficiently far away from each other, so there's not massive overlap. And third, there's some coverage property. So any point pi is quite close to one of the any point z in the manifold is quite close to one of the points pi. So all these properties. So we have this collection of disks. So now what do we have to do? Now we want to do some fine tuning. So these disks are at a scale. I'm going to now replace that unit thing that I said by square root of sigma. This is the actual scale. So you have to choose them to be roughly square root of sigma. We pick these disks. Okay, so we have this family of disks that that kind of look like the manifold at a coarse scale. What we want to do is do it at a finer scale. So what we're going to do is take these disks, take a lattice on this disk at a length scale of sigma rather than square root sigma. Now sigma is already very small, so sigma looks much smaller than square root sigma. So we have this lattice, and now we take a Voronoi partition of this disk, and then we look at all the points in this ball. So all the blue points that you see here are contained inside a ball, and we put them in the buckets. So these Voronoi cells are like buckets. You put them all in corresponding buckets, and when you look at all the points in a given bucket, you look at their mean. Okay, and then you get 1 point at a scale of sigma. And you do this for the other buckets as well. So now you have got a fine net at a small scale. And then we fit disks again to this new data set. So earlier we had these blue points. Now we're going to have a set of brown points. You fit a new set of disks of a smaller radius, roughly sigma, to the new data points. And when you do this, you will be able to manage a Hausdorff distance of order sigma squared, rather than just sigma. So the idea of why you gain a sigma squared over a sigma is that if you have a C2 function and you move tangentially by sigma, then the amount by which you move from the graph, the function is roughly sigma squared because of the second derivative. So that's where the sigma square comes from. Okay, so this is the picture. We got this sigma, and you put disks of scale sigma. And now what do we do with all these disks of scale sigma? So this is where the analysis comes in. So we are going to use some so-called partitions of unity and patch up with these disks of scale sigma. These are like functions of the form ci 1 minus v squared raised to d plus 2, and they form these bumps that kind of cover the manifold, and they are useful in patching together little pieces. So could somebody please tell me how much time I have left?
Yeah, so you have about 10 minutes.
10 minutes. Okay, thank you. I can go into some detail. All right. So yeah, thanks.
Sorry, 8 minutes.
Oh, okay. Okay, thanks. Okay, so these functions are as you see. So this is to be viewed as on a disk. This is on a disk of or on a ball of some dimension. Yeah, but you see the d plus 2 is tuned to the dimension, so we need to know the dimension in advance. And 1 minus v square is going to be tapering off. At v equal to 0 it is 1, at v equal to 1 it is 0, and thereafter it is always 0. It's 0 otherwise.
Moi j'arrive à sortir et re-rentrer, mais par contre j'arrive pas à aller dans un autre.
Sorry, there was some disturbance again.
Sorry.
Yes, please continue.
Yeah. So these alpha tilde of x, these are the sums of these bump functions. Okay, so there are the sums of bump functions, and one has to carefully arrange that this normalized functions. So these are the normalized functions. One has to carefully arrange that this alpha tilde satisfy some lower bound and upper bound. Okay, so this one has to do. So for this one basically has to take some sort of Voronoi cell again and carefully choose the radius of the bump functions with respect to the diameter of the cells. So this is some delicate things one has to do. But in the end of the day, the estimate we need is just this, that alpha tilde of z, which is the sum of all the bump functions, lies above and below some nice constants. So here is roughly the picture. The black manifold is what we wish to construct. It's not there right now. We have all these red disks. And from all these red disks, we wish to construct the black manifold. So together with these red disks, they come with these vector fields. What are these vector fields? They simply are they're normal vector fields. They increase linearly up to a point. So up to some radius, let's say related to the reach, which we have given some a priori bounds on. Okay, so you have all these vector fields, and so from these vector fields you can superimpose using the bump functions. So you multiply this by a bump function, add up, and what you get is another vector field which kind of looks like the normal vector field to the manifold. It is approximately like that. It's not exactly like that because you started with these disks which are not exactly the manifold. And anyway, so it's not exactly that, and that this is the source of the whole problem. So we have to do something careful in order to get an actual manifold. And what is that careful thing? The careful thing is we start with these FIs are the vector fields. Okay, these FI are the vector fields that I showed for different things, different pieces. Alpha I are the bump function. So this is a master vector field F. Once we have the master vector field F, then we have to produce an object from the Hessian of not Hessian. So I'm sorry. So this pi I is the projection onto the ortho complement of the disk. Okay, that's what the pi I is, the projection onto the ortho complement of the disk. I'm going to take these matrices and I'm going to combine them using the alpha I. Since they are almost parallel, I'm going to get something that is almost a projection matrix, but not quite a projection matrix. Once I get this almost projection matrix AX, I'm going to convert it into an actual projection matrix by only preserving the large eigenvectors for large eigenvalues and truncating all the small eigenvalues to 0. So then I get a projection matrix pi x. And once I get this projection matrix pi x, I define the manifold to be all those points x such that pi x f of x equal to 0. So this is a closed form expression for the manifold. It's not it's an implicit expression. It's not explicit in the sense that it's not like a function whose image is the manifold, but it gives you a criterion for determining whether a given point is on the manifold or not. And this criterion can even be used to know if a given point is close to the manifold or not, simply by seeing how close to 0 this expression is. Okay, so here is the picture. So these are these projections onto these normal, these are the pi i's, projection onto the normal pieces. They're patched together, and then you construct a pi x. These are the pi x's actually. So that as you see, they turn slowly, and then you use them and f of x to determine the manifold. This is the main theorem, and in the meantime, pi x is, what I mentioned is not a very effective way of producing pi x with computing pi x and truncating and all, because we need to take derivatives of pi x and so on and understand how it behaves, because we need control on the reach of the resulting manifold, which is given by pi x f of x equal to 0. So for this reason, we need an algebraic expression, and indeed there isn't such an algebraic expression that obtained from Cauchy's integral formula applied to the matrices. Okay, so this is true, and this can, and then we also use Holder inequalities to get the bounds that we decide. I mentioned that we have to do extra work to get a polynomial in D in the denominator in the reach. So these Holder inequalities are used. If not, you would not have got, if you didn't use these, we would not have, we got a polynomial bound, we would have got an exponential number in D. So this is defining the output manifold, and one has to use a quantitative version of the implicit function theorem, so which are probably well known, but one that gives bounds on the curvature of the surface that it guarantees. So that is this quantitative implicit function theorem. And to conclude, we bring down the Hausdorff distance between the true and output manifolds to order sigma squared d by tau, while bringing down the sample and computational complexities to depend only on the intrinsic dimension when the manifold is C2. Some open problems are: when k is larger than 2, can we do better if the manifold is Ck? Are there suitable conditions under which one can learn manifolds even when sigma, the noise is very large? So with these, I will stop. Thank you for your attention.
Thanks, Hari, for your talk. So are there any questions for Hari? Are there any questions in the chat? Does anybody have? Let me go over the chat. I don't see questions. No?
I don't think there are any questions in the chat, KV. I didn't see any.
Yeah. So finally, so I have a question. I mean, it's a very layman kind of question. I don't know much about what all this is about actually. So finally, you got because I mean, you going back to your original thing, everything was really coming from this virus, and you had this huge manifold from which you want to reconstruct, in some sense, the three-dimensional sort of manifold, right? Is that how I should view the problem?
So that was a toy problem. Unfortunately, with the virus, there is an additional level of difficulty. This will help you denoise. So actually, the images are noisy. So this procedure will help you produce something that is very close to the actual projection, actual images that the cryo would have produced without the noise.
Okay,
but then there is the additional step of having to reconstruct the 3D molecule structure from the 2D, 2D
projections.
projections. Yeah.
Okay.
So that I have not, of course, talked about.
Okay.
Harry, I had also a layman question. You talked about, I mean, this is a rather complex procedure for getting this smaller manifold. You said sometimes the manifold hypothesis doesn't hold, and I remember an article a while back where there was some discussion of that, but can you tell us, roughly what are the bounds of this method? What stops us from doing this dimension reduction all the time?
Yeah. So the things I told you only will work if the little d is quite small. So maybe, less than 5.
Right.
So that is certainly not true in images and things like that. It's I think people say it's closer to 100. There are other structures in it, but if you just look at the plane dimension, the dimension in the space of images is quite large, is my understanding. I don't know this very well, but I think so many real data sets do have larger dimension. So then one has to try other things, I think.
Okay, and I mean, so in the case of if we could have some sort of, if we knew antecedently that, say, an image, or what I work on is language, had some sort of antecedent structure, some sort of algebraic structure, that's kind of what you were doing with the virus example. You knew that it had a certain kind of algebraic structure. If we thought that scenes, visual scenes, had a kind of algebraic structure, some sort of even grammar, we could maybe exploit that in this case to get the dimension down. Is that correct?
So that is correct, but it is not the way I was looking at things, because when you start looking at grammar, then supposing you're moving into the discrete realm, and everything I've been talking about is very continuous. But
right,
I think, so there are these things like word to vec embeddings, which I don't know much in. So, but it's possible that maybe even things that actually are discrete can be viewed as some continuous object, and then they can be analyzed with such methods. So that is also a possibility.
Yeah.
Exactly. Yeah. Thank you. That's where I was going with this. Right.
Sounds good. Yeah. Okay. Are there any more questions for Hari? No. So then let's thank Hari for a lovely talk. Yeah. Thank you, Hari.
Yes. Thank you very much. Very inspiring.
Yeah. So next speaker for today is Purushottam Kar. So Purushottam is a PhD from IIT Kanpur. So he worked with Harish Karnik and with Manindra. And he has also done a lot of work with Pratik Jain. In fact, they have a lovely book together, I think. A book that I have used twice when I've taught the course. Yeah. So Purushottam will be talking to us about using high school geometry to defeat adversarial attacks on learning algorithms. Purushottam?
Yes.
Yeah.
Yes. Thanks, KV, for that very generous introduction. So I'm being told that I cannot share my screen while someone else is sharing.
I'll just make you co-host.
Yeah, but I think Hari will have to stop his screen.
Hari, you'll have to stop. Sorry. Hari. Hari. Yes.
Hari, you have to get rid of your, stop sharing your screen. Yeah.
Yes. Okay. Yeah. Let me get Purushottam on. I've lost your
are you able to see my screen now?
Yes, it's fine. Thank you.
No. Yeah, now it's coming. Yes, now it's coming. Yes.
Okay.
Yeah.
So let me know I can start at any point.
Yeah, you could actually start. It's 3:05, I think, by my talk. Yeah.
Sure. Okay. So hello, everybody. Today I will show you a method to protect machine learning algorithms from attack. Before digging in, let me tell you a bit about myself. I have a keen interest in the foundations of machine learning, such as learning theory and optimization. I also developed classification algorithms that can scale to applications with millions of classes. These are super useful in ranking and recommendation systems. I have developed a close interest in using machine learning to improve air quality monitoring, as well as tools to help teachers like me manage classes with several hundreds of students. I warmly welcome an email from you if I can help you in any of your projects. So now let's get back to business. Let's see how evil people attack machine learning algorithms. A typical ML pipeline consists of training data being fed into an algorithm, which performs the learning to generate a so-called model. This model can now make predictions on new and unseen data points. The algorithm and the model are often considered safe from direct manipulation, as indicated by these locks. However, these locks are not impenetrable. Firstly, it is possible for an attacker to steal the model by asking a lot of random predictions to be made on a huge large number of data points. This is a fascinating form of attack known as model exfiltration and can result in privacy breaches as well as monetary loss to companies. Secondly, it is possible for an attacker to poison some of the data points being used to train the model. A good example is fake reviews on e-commerce websites. By poisoning the training data itself, the adversary can force the algorithm to learn a model of its choice that will give predictions the adversary wants. In this talk, what I will focus on is protecting ML algorithms from data poisoning attacks. Now, although it might seem that the attacker must poison all the training points to execute its evil plan, this is not the case. Most machine learning algorithms are so brittle that poisoning just a single training point can drastically change the model being learned. Case in point is a story example of good old linear regression or line fitting. Even a single change to a training point, just one training point being changed precisely, can vastly alter the slope and intercept of the line being fit. Now, many ways have been proposed over the years to counter data poisoning. Let's have a very quick look at some of them. In the subset selection approach, the machine learning algorithm tries to guess which points were poisoned and performs learning after excluding those points. Afterwards, the guess is updated and the process is repeated. It is hoped that eventually the algorithm will be able to correctly guess all the poison points and perform learning only on the remaining clean points. The reweighing approach is a generalization of the subset learning approach, where instead of including or excluding data points, weights between 0 and 1 are assigned to each point to indicate how likely does the algorithm think the point is poisoned. These weights are updated repeatedly to reflect the algorithm's changing opinions. The aggregation approach looks a bit like gerrymandering, to be honest. The trick is to divide the data into subsets and learn a different model on each subset, and then aggregate all these different models into a single one. The hope is that some of these subsets will have less or no poisoned data points, as is indeed the case in this toy example. And consequently, the models learned on them will be clean. And the hope is that those clean models will then dominate during the aggregation step. The reformulation approach is a very popular one, and it uses powerful optimization techniques to first cast the learning problem as a combinatorial problem and then as a numerical problem. For example, if we want to solve this toy line fitting problem with 3 poison points, you can first cast it as a combinatorial problem to fit a line with such that it agrees with at least 7 points, because suppose we priori know that 3 points were poisoned. But we can then convert it into a more numerical optimization problem of absolute deviation minimization, which can be solved very easily. And the solution to these numerical problems can often be rounded off to obtain a solution to the original problem. Now, in the remainder of the talk, what I will describe to you is a new approach to tackle data poisoning called incoherence. My collaborators and I developed a method called APIS using this approach. You can read more about it in our paper, or you can even download the code from this GitHub repository and play with it. The code is very well documented and it has examples to help you run corrupted or poisoned data attacks and see how the algorithm responds. Now, to explain our method, I need to set up some notation. Let the n-dimensional vector A star denote our clean signal, which gets poisoned by another n-dimensional Poisson vector B star, so that what we see is the vector y equals to A star plus B star. For example, in linear regression, A star is simply the responses or the labels of the n training points, so that A star is x times W star, where x is the n cross D matrix of data features, and W star is the underlying linear model. Note that B star would be 0 in locations corresponding to data points that did not get poisoned. Now, also note that we do not know W star. All we can see is y and x. And given this, we want to recover A star. We can also recover W star, but once we recover A star, recovering W star is pretty simple. Now, for reasons I'll not get into right now, it's important to restrict the adversary in some way for recovery to be possible. For example, we could say that the adversary is allowed to poison only k of the n data points, where k is less than n. The adversary can choose which k points it wants to poison, but only k are allowed. The APIS technique that I will describe to you will allow us to way to recover A star if the vectors A star and B star lie on nice subspaces. To describe this method, I will remind you of two concepts that we have known since high school, that are subspaces and projections. Now, if you have never heard of the term subspace before, just think of them as planes in high dimensional spaces. For example, we could have a one-dimensional subspace that are just that's just a line, or a two-dimensional subspace that is just a plane, or you can even have three-dimensional subspaces, and so on and so forth. For this talk, we may also need to work with unions of subspaces, which are just a collection of lines or a collection of planes. Nothing fancy about that. Now, you might wonder, why are subspaces coming into the picture? To see this, recall that in linear regression, we had A star equal to x times W star, where x is the feature matrix. This means that A star is a linear combination of the columns of x. Now, we don't know what is that linear combination, because that depends on W, and we don't know W. However, we are sure that A star can be written as x times some vector v. That vector v just happens to be W star. This means A star lies in the columns of space of x. So that's why subspaces are important for our work. Next question, why are unions of subspaces required? Now, they are helpful in many ways. One of the ways they can help is when we know that a vector belongs to one of many subspaces, but don't know which one. So in this toy example, we have 10 points, 7 are clean, 3 got poisoned. So which means B star has only 3 non-zero entries. Now, if we knew which data points were poisoned, then we could say that, see, B star belongs to this specific three-dimensional subspace spanned by these 3 specific canonical vectors. But we don't know B star. We would have loved to know B star, but we don't. All we know is B star has some k non-zero entries. We don't know which k. So which means that B star belongs to one of n choose k possible subspaces, but not which one. That's why unions of subspaces are useful to the discussion. Now let's talk projections. Projecting a point onto a set simply means finding a point in that set that is closest to the point being projected. So you have a point P, you want to project it to a set A. You simply try to find a point Q in that set which is closest to P. Now, projections are nothing new to us. And since high school, we have seen how to project all sorts of objects like lines and points and line segments onto hyperplanes. So here are 2 simple examples. Projections onto subspaces and projections onto even unions of subspaces can often be done efficiently. For example, projecting onto the column space of the feature matrix X it requires solving a least squares like problem. So it can be done rather efficiently. So now we have all the ingredients to describe the APIS method. Now, suppose we are given y, which is the vector we observe. Remember, y is equal to a star plus b star. A star is the true signal, b star is the Poisson vector. Suppose we are additionally told that a star belongs to a set A and b star belongs to a set B. For example, in the linear regression case, A is the column space of X. The sets A and B could be subspaces or unions of subspaces. And now suppose my friend comes and tells me that he has a vector AT with him that he knows or is very sure that is very close to the true signal A star. Now, so I believe my friend, but now can I use this to get a reasonable estimate of the Poisson vector B star? If I think for a moment, since B star is equal to y minus A star, and my friend tells me that AT is close to A star, then it must be the case that the vector, let's call it B hat T equals y minus AT, must be a good estimate of B star. Fine. There is a slight complication here that B hat T may not lie in the set B, but that can be easily fixed by projecting onto the set B. So we get a new vector BT. That's our estimate of B star. Now, what prevents us from repeating this process again and again? Nothing. So we actually do that. Using this new estimate of B star, we get a new estimate of A star. And if it so happens to not lie in the set A, we project it onto the set A to get our next estimate AT plus 1. And we keep doing it again and again and again. It turns out that if we repeat this sequence of alternating projections, we are guaranteed to move closer and closer to A star with each iteration if the sets A and B satisfy a property called incoherence. This brings us to incoherence. Now, the English word incoherent means unclear or not understandable. For example, drunk people usually speak incoherently. Two subspaces, A, let's say A and B, are said to be mu incoherent if taking a vector A, taking a vector in the subspace A and projecting it onto B reduces its length or Euclidean norm by a factor of mu and vice versa. This means that these subspaces don't talk to each other very well. So in this example, we have a two-dimensional subspace A and a one-dimensional subspace B. And as you can see, they are nearly perpendicular to each other. This means projecting any vector u in A to B will almost kill off the vector, make its length go to almost 0, which means they are mu incoherent with mu very close to 0. In contrast, in this right-hand side example, we have a pair of subspaces A and B, which are nearly parallel to each other. Projecting a vector u from A onto B will hardly change its length, which means these subspaces are coherent. They are mu incoherent, but with mu very close to 1. So they're not very incoherent at all. So in summary, what the APIS algorithm does is it takes the Poisson signal and the sets A and B to which these signal and Poisson vectors are supposed to belong and performs alternating projection onto these subspaces to on these sets to obtain its final output. What we can show, and I won't be going to the proof here, is that if the sets A and B are mu incoherent with the incoherence constant less than 1/9, then APIS can provably recover A star at a linear rate of convergence. Some more calculations show that APIS allows ML algorithms such as linear regression to be carried out even with a constant fraction of the data points getting poisoned. Although we don't have time to prove these results, we can still try to get some intuition as to why this theorem should be true. So consider a toy setting where we have A and B are these one-dimensional subspaces. That means there's lines. As you can see, these lines are sufficiently non-aligned. They're not perpendicular, but they're not parallel either. So they're sufficiently incoherent. There's a large angle between them. And this is my A star and this is my B star. So what I get to see is Y equals A star plus B star. Good. Let us start running APIS. So I need an initial estimate, but my friend is not picking up his phone. So I take the initial estimate of A star to be 0. Why not? Let's do that. Which gives me B hat 0 as Y minus A0, which simply is Y. Now what do? Y doesn't belong to B. So I need to project onto B to get my initial estimate of B. So this is my initial estimate of B. Note that this estimate lies a bit far from B star, so not a very good one, but never mind, let's continue. Next, what do? I get my next estimate of A star, which is by simply Y minus B naught gives me A hat 1. So I get my A hat 1, but A hat 1 doesn't lie on the subspace A, so I simply project onto A to get my next estimate. This estimate, as you can see, seems to be reasonably good. So we are warming up. So let's keep going. If we keep going and doing these iterations, we will see that both A star and both the estimates of A and B that we have keep getting closer and closer to their respective true values. So we are already in the second iteration. Just a couple of more animations and we are done. So we saw that these iterates kept approaching their true values at a very, very nice rate. In fact, A3 has almost reached A star already. This is no accident. In fact, that's the key to the proof that what we can show is that every time we do a projection, a constant portion of the remaining Poisson gets destroyed because of incoherence. Now, that's all I have to say about the proof. I won't be going into the proof. So, but let me show you a few ways in which APIS can be applied to perform recovery in Poisson settings. So APIS is easy to implement and the code is publicly available. You can download it and play with it. We tried running APIS on a few tasks. One of them was linear regression tasks with up to 20% of the data points getting poisoned. APIS could offer exact recovery with up to 10 times faster convergence than leading methods that also deal with data poisoning. So data poisoning attacks are a very, very well studied area. So APIS offers very fast recovery. However, the main bragging point for APIS is that it's also able to extend to not just nonlinear, but indeed non-parametric regression tasks with, again, provable convergence guarantees. So for non-parametric tasks, non-parametric regression tasks like kernel regression, APIS could offer up to 10 times smaller test root mean squared error than existing methods. APIS also has we also found quite serendipitously a nice application of APIS to image denoising, where it was able to recover poisoned images using techniques such as robust Fourier transform. So what we did was we took an image and we poisoned it using, in this case, salt and pepper noise. We found that APIS offered a much higher recovery quality than leading techniques, which include signal processing techniques as well as deep learning techniques such as denoising CNNs. Notice how APIS was able to recover back fine details of the image, such as the tablecloth pattern and the stripes on the clothes the lady is wearing. In contrast, the denoising CNN was able to do a very good job of recovering the image, but in the process, it also blurred out many of these fine details. But APIS was able to preserve those fine details. Here is another example of a nice image of a butterfly, which was also poisoned using salt and pepper noise. And again, we can see that APIS offers very sharp images as recovery, not a blurred one. The difference between the advantage offered by APIS is significantly more when we come to poisoning, which is done in a structured manner, such as using a watermark. So what we did was we imposed a checkerboard watermark on the images. So here the difference is night and day. APIS offers a significantly better way to recover the image. Also, you can still see some artifacts of the watermark, but the recovery is far, far better than the other methods. Same with the butterfly image. By the way, these are just two images that I'm showing here. If you look at the GitHub repository, you will find, I think, about a dozen such images. They're a part of a standard data set. So we can see, you can play around, run APIs, try to break it, try to improve it. All that can be done. I think this is a good point to stop. I would be happy to elaborate on any of the points I made and answer any of the questions. Thanks for listening so far.
So if you have questions,
Thank you very much for the talk.
lovely talk.
Oh, MS, you have a question. Mandayam.
Yeah, it's a very nice talk. Okay, the slides and so on. See, the question I ask, maybe it may not be related to the exact work that you do, but are there any kind of, in your method when you do the final outcome, are there properties that your final decluttered image must necessarily satisfy or not satisfy? I mean, are there certain properties that you would like your algorithm, APIS, to preserve or not violate? Okay. Are there certain those kinds of things that you might have thought of? Okay, that might be worth checking for your algorithm.
Thanks for the question, Mandim. I can see what you are trying to ask. Maybe let me try to answer it in two ways. One, what we do right now, and second, what could be done. So first, what we do right now. Right now, the only property of the image that APIS tries to preserve, that it must have a sparse representation in the Fourier, or let's say the discrete cosine domain. So when we do a Fourier transform, natural images usually don't use up the entire spectrum. They usually have very sparse or truncatable spectra. APIS tries to preserve that. But what could be done, and I think that is where you were hinting at, is that if we know that certain aspects of the images are worth preserving, can we bake them into the model? Yes, that can definitely be done. We don't do it right now, but in some sense, in the Fourier spectrum, we just look for sparsity. We don't care which coefficients turn on, so long as not too many of them do. But we can definitely go for structured sparsity to preserve more and more desirable properties of the image. In fact, that is one of the things we tried to do a bit theoretically in the paper, but experimentally we weren't able to do yet. Does that answer your question?
Yeah, it does. Thank you.
So there's a question on the chat for you.
Yes, any advice for 18-year-olds?
Does that refer to the high school aspect of the title?
I think so, maybe.
No, it just means that, I mean, I'm not one of those people who said like, no, people should start teaching machine learning to 5-year-olds and all. No, I think students in high schools are already loaded with a lot of work. Let them enjoy their childhood. But it just means that it can be accessible to them.
I have a question for you, Purushottam. So this bound on mu, I mean, it means that the spaces have to be really pretty incoherent in your theorem. And so what happens when mu is closer to 1? Is it just that it takes longer to converge, or does the theorem really fall apart? I didn't know.
Yeah, that's a very good question. So we can improve the bound on mu for special cases. For example, if either one of the sets A or B is not a union but a single subspace, then this bound can go up to 1/3 from 1/9. So it's a more relaxed bound. But to answer the more general question, no, we don't know yet what happens when the theorems stop, when the theorems fall silent. Is there a graceful degradation? We feel that is the case because experimentally, when we try plotting these breakdown points, we don't get an immediate breakdown point. We just get instead we get a band of degradation, after which it's all mayhem.
It's all mayhem. I see. Okay, because my intuition would be that it is a graceful degradation. It just takes longer and longer to converge. But you're saying, in fact, maybe not, and that's interesting.
What is also so there's also one other thing that is there in our experimentally verifying these breakdown points is a bit hard, because it's genuinely difficult to simulate an adversary, because in our theorems we assume that the adversary is this all-knowing, computationally all-powerful thing, but it's very difficult to actually do that in practice. So we don't even know whether our adversaries are truly living up to their potential or not.
Okay, thank you. Very interesting.
Yeah. Any more questions from Purushottam? I think
there's one more.
Yes, there's one more in the chat.
Or actually two. DM and DB.
How do you figure out the sets A and B for some of the examples you talked about? Is there a way to do it systematically?
Yes, I'm sorry, I did not touch upon this at all. In the examples, in all the examples that we saw, A and B are, the sets A and B are implicitly described to us. So in the linear regression case, one was the column space of the feature vectors. The other was this union of subspaces of sparse corruption. So we knew that some K elements are corrupted. We don't know which one. That implicitly gives us a union of subspaces. Even for the image recovery case, the set A is the set of all signals that have a sparse Fourier transform, because we know and believe that natural images do have that property. So in all the cases we looked at, these sets can be described. I'm sorry, I didn't go into this in the paper. The paper in the talk, the paper has all these details.
Oh.
I think there's someone else who wants to maybe ask a question.
Yes, please go ahead and ask.
Yeah, so I was wondering that you said that you can also extend this method to a space which is non-linear, right? As in like y is equal to f of x w plus b star.
Right.
Right. So in that case, it seems quite close to something like mirror descent or like something like that. So was it related to something like that? Maybe.
So I'll be honest, the extension to non-parametric regression is a bit of a, I won't call it a cheat, but a bit of it, and there's non-trivial work to be done. But basically we use the kernel trick to to extend the results of linear regression to non-parametric regression. So if you know about the kernel trick with Mercer kernels, you would know that that allows you to effectively do linear stuff in the RKHS. The algorithms don't have to change much, except they may have to run in the dual and stuff. But you conceptually you can think of them as working in a linear domain. So that was the idea. We did we have not tried with splines or those sorts of nonlinear function spaces. That is something that we are interested in doing right now.
Okay, thank you. That answers my question.
Thanks.
Okay, so then let's thank Purushottam. Thanks, Purushottam.
Thank you very much.
So third, So our third speaker for the day is Edward Powells. I hope I've said the name correctly. So he'll be talking to us about non-smooth backpropagation for learning algorithms. So his interests are primarily numerical optimization And so in fact, I've gone to his web page and I see that he has a lot of stuff on numerical methods for machine learning and applications in automatics and biology. So, Edward?
Yes. Thank you for letting me present this work here and for organizing this very nice workshop. So indeed, I'm going to talk about non-smooth backpropagation, the main motivation being application to deep learning. This is joint work with my colleague Jérôme Bolt, and we are both from Toulouse. So first, what is backpropagation? Backpropagation is a way to differentiate functions given in the form of compositions. So if f is a function with values in R, given in the form of composition of differentiable function, backpropagation is simply an efficient algorithm to implement the chain rule. So the chain rule says that Jacobians of compositions are compositions of Jacobians, or if you like, matrix multiplication, because Jacobians are matrices. And simply the Jacobian of a function is the gradient transpose. So backpropagation is a way to compute gradients, provided that we have Jacobians. There is a very nice theory underlying this backpropagation algorithm. So naively, we would think that computing the gradient of a function f would be p times the cost of computing f, because we need to compute p-values. Okay, so there is an underlying model of computation here. I'm not going into the details. And there is a nice cheap gradient principle by Bauer and Strassen, which says that actually the cost of computing the gradients is bounded by a constant time the cost of computing. And the underlying idea is precisely the backpropagation algorithm. Furthermore, from a practical point of view, backpropagation is essential for training neural networks. And so it's one of the backbones of TensorFlow libraries and other similar libraries for deep learning. The issue here is that we need non-smoothness because for many applications, the elementary functions, GIs here, are non-differentiable. So one of the main examples is relu, but we have more complicated examples. Okay, so first, let's see how to define a generalized gradient for non-differentiable objects. So this is the idea is due to Clark. We'll consider a locally Lipschitz function f. So for example, the one here. And there is a famous result in analysis by Rademacher, which says that it has to be differentiable almost everywhere. So here is differentiable everywhere except at those 2 points. So the idea of Clark is to consider limits of neighboring derivatives. So I have derivative almost everywhere. I can take limits. So for example, here, if I come from the right, I'm differentiable and I have a limiting tangent. Here, similarly, I can do the same from the left. And there is a convex hull on top of all this. Okay, so I take convex hull of neighboring limits of neighboring Jacobians. So in the case, so this is called Clark Jacobian, and the index C here is here to explicit the Clark name. And in the case of a function with a single output, we will talk about Clark subgradients. Okay, and the notation partial denotes subgradient here. And it's important to keep in mind that this is a set-valued map, meaning that this is a function which takes values in subsets of matrices. And we will denote set-valued map by those double arrows here. So it's not single-valued, it's multi-valued. So this is classical. For example, in convex analysis, these are the type of object that we consider. Now, how does non-smooth backpropagation work in practice, given this object? So we get back to our composition. F is given in the form of composition, but this time F is, say, Lipschitz, and the building blocks are also Lipschitz. So examples, again, relu and other functions. So in this case, backpropagation is a formal application of the chain rule. Okay, so we may consider the product of the Clark Jacobians. So this product is a set-valued product, meaning that we consider all possible choices of elements in the Clark Jacobians and multiply them. This gives a set of matrices, and backpropagation actually outputs an element of this set. Okay, so it chooses one element in each generalized Jacobian and perform the multiplication. So that's one way to phrase it. Another equivalent way to phrase it is that backpropagation will be a function from RP to RP, which is a selection in the set-valued field, which consists of multiplication of generalized Jacobian. Okay, and this is actually modeling the reality. This is what is happening in TensorFlow, PyTorch, JAX, etc. So they compute selections of this product. So this begs the question: what is this product? What is the output of backpropagation, and can we say anything about this product? What kind of gradient could it be? Okay, so the starting point of this investigation is to realize that the output may be quite unpredictable. So let's illustrate this with very simple examples. So that's the ReLU function, which we've been talking about. And those are two variations around the ReLU function. And it turns out that you may do the computation, those functions are the same. So mathematically, they are the same function. They provide the same outputs for any t. Okay, but if you implement these in TensorFlow and ask for backprop, then for the first one, at 0, you will get value 0. For the second one, at 0, you will get value 1. And for the last one, at 0, you will get 1/2. So this highlights the fact that the output of backpropagation depends on the program, depends on the implementation. And it's not only dependent of the function itself. It depends on the way we implement it. So far, it's not too bad, but it could be much worse because in the non-convex world, we are allowed to do nasty things. And for example, I could implement this function, which I call 0. The reason I call it 0 is because the output is constant and it's 0. However, backpropagation applied to this function says that the derivative is 0 everywhere except at 0 where it is 1. Okay, so this doesn't have any variational meaning. This is a pure artifact of non-smooth backpropagation. And we could play with this further. So for example, if I choose any constant s in R, then the backpropagation applied to s times 0 will be s. So I could get any value that I choose. And I can actually create a critical point, artificial critical point with this. So for example, this is a nasty implementation of the identity function. So it is effectively the identity. However, backpropagation at 0 gives 0. So I create an artificial critical point, a point where the gradient is predicted to be 0, but this doesn't have any meaning because, of course, the true gradient of identity as 0 is not 0. And this could have important practical consequences because if I initialize, say, a gradient descent algorithm with backpropagation in place of gradients, if I'm unlucky and I initialize at 0, essentially I do not move. Okay, so this has consequences for algorithms. Okay, so this unpredictability is well known from non-smooth analysis, and it's related to the absence of calculus for generalized derivative. In general, if I have two Lipschitz functions, then the subgradient of the sum will be contained in the sum of subgradients. So that's an inclusion, but the inclusion could be strict. Okay, so let's see some examples. First, equality cases. If I have continuously differentiable function, then of course this is an equality. This goes beyond. If I have convex function, this holds with equality. And if I have subdifferential irregular function, which is a slight generalization of convexity, I still have equality. However, in general, I don't have equality, and you have very easy examples. If G is the absolute value, then G minus G is 0, and the subgradient of 0 will be the singleton 0. However, the sum rule predicts that the subgradient at 0 will be the whole segment minus 2, 2. Okay, this is a segment addition. And so this is the main mechanism, the main mechanism in the examples that we have seen before. Okay, this is well known in non-smooth analysis. The issue is that in deep learning, we are not in position to assume any of the first three sufficient conditions to treat the general cases. So as I mentioned, we have many non-smooth examples, and for those non-smooth examples, convexity is not a reasonable assumption. So we need to make sense of calculus rules taking into account this kind of artifacts. Okay, so what we have seen so far is that backpropagation is a selection in a somehow enlarged subgradient. The fact that we have an enlarged subgradient may produce some artifacts, and we have non-unicity issues. Different programs may implement the same function but gives different results when it comes to backpropagation. And to push it a bit further, this may also have implication for stochastic approximation algorithms. So, for example, SGD. Okay, so what we would do to minimize a sum like this would be to compute the subgradient of the sum. However, this would be contained in the sum of the subgradient, the average of the subgradient. when we do stochastic approximation, we effectively compute in expectation something which belongs to the right part of the inclusion and not something which belongs to the left part. Okay. So what do we need to do? There is a very important remark at this point. Despite those artifacts, non-smooth backpropagation is used a lot. It's a massive practice, and it actually works very well. So it's a very good asset in terms of learning, numerical libraries, etc. So we need to understand why and provide guarantees for training mechanisms and tools for eventually for robustness and sensitivity analysis. From a mathematical perspective, this means that we need to understand the variational content of backpropagation and eventually its relation with the gradient whenever the gradient exists. We also need to understand what are the critical points of backpropagation. What does it mean to be a critical point or a steady state? In terms of optimization, we need to understand the consequence of using backpropagation in place of gradients or subgradients in algorithms. And in general, we need to develop a non-smooth backpropagation calculus to treat all issues related to non-smooth neural network, training, robustness analysis, etc. Okay. So let's see a first idea, a first possibility. The first idea that we would have, that we had actually, is to build a multi-valued backpropagation operator. So the idea is Clark's subgradient is maybe too small. Let's construct an operation, a generalized gradient, which will be potentially larger and compatible with backpropagation. So what does it mean? It would be an operation on Lipschitz functions. It would be given a Lipschitz function, I will construct this generalized gradient, and it should satisfy the following. So it should contain the output of backpropagation applied to f for all Lipschitz functions, and it should be compatible with the chain rule, so the Jacobian multiplication rule. And so based on the example that we have seen before, it's actually possible to show that no such non-trivial operator exists. Okay, so there is no subgradient operation which is completely compatible with backpropagation at this level of generality. So this is not something that we should try to do. So we need to resort to something different. And what we are going to do is we give up on this operator perspective, and we are only going to describe relations, properties of the relation between a function f and its derivative. So that's how it goes. F will be a Lipschitz function, and on top of each input x, we put a set. So dfx will be a subset of f. Okay, this is the set of generalized gradient. For the moment, it's arbitrary. So actually, there are technical assumptions. df will be a set-valued field, and it needs to satisfy some technical condition. Okay. What we will ask here is the following. This is the chain rule along absolutely continuous curves. Okay. So for any gamma absolutely continuous, gamma will be differentiable for almost all t, so this makes sense for almost all t, and f composed with gamma will also be differentiable for almost all t, so the equality here makes sense for almost all t. The thing that doesn't make sense for the moment is the dot product, because I'm considering the dot product between gamma dot and df, but df is a set. So what does it mean, the dot product here? It means that the equality should hold for all d in the set df. Okay, so I want for all d in df, the dot product to be constant, and this constant to be equal to the time derivative of f composed with gamma. And this has to be true for almost all t. Okay, so this is chain rule along differential calculus, along absolutely continuous curves. In this case, df, the set valued field, will be called a conservative gradient or a conservative field. And at this point, it's important to realize that it doesn't define a unique df. For example, if I change the value of df at one fixed x, only one, then this relation will not change. It will still be valid. So there is actually an infinity of such df, potentially, which if one exists, I can construct many other such dfs. Okay, so where does this come from? This is a reminiscent of what we have in the differentiable world. If I have a function f with Jacobian gf, then we have the same property. This is the chain rule along differentiable curves, and it holds for all t. Okay, so it's a reminiscent of this. And the non-smooth extensions of this thing have been proposed in similar form by Brezis, for example, in the convex analysis setting, and Valadier with the notion of sen function, which is quite close to what we are investigating. Okay, so that's a conservative gradient. The nice thing about this is that it brings back calculus. Okay, so as I mentioned, we give up on the operator view, we give up on unicity of the generalized derivative, but we still have calculus. So this takes form of the following proposition. If I have conservative Jacobians, then I may compute linear combinations, and this will still be a conservative Jacobian. And if you remember the examples in the introduction, this was something that was missing for subgradients. Okay, linear combination of subgradients are not subgradients in general, they can be different, but when it comes to conservativity, the property is preserved. And actually, we have a composition rule which is much stronger than just linear combination. We have a Jacobian product rule for conservative Jacobians. So that's the equivalent of the usual chain rule for Jacobians in the differentiable world. So we can multiply conservative Jacobians and preserve the conservativity property. Okay, let's see a few properties of those conservative Jacobians. So first, a conservative Jacobian almost everywhere has to be a singleton equal to the true Jacobian. Okay, so that's a nice property. It cannot be too wide. It has to be almost everywhere equal to the true Jacobian. And as a consequence, we could see the Clark Jacobian, okay, so the Clark subdifferential, as a minimal convex conservative Jacobian. And this is a consequence of the previous result. For any conservative Jacobian JF, the Clark Jacobian of the associated function f will be contained in the convex hull of JF. So it's a kind of minimal conservative Jacobian. And in particular, it should be conservative provided that there exists a conservative Jacobian JF. And actually, pushing this further, so this is a result which is due to Lewis and Tian in 2021. The conservative Jacobian JF has to be close to the Clark Jacobian, meaning that there is an inclusion, a broader inclusion on the right here. So it has to be contained in the Clark Jacobian plus an object which is small, which we call residual. So it has to be small, and the definition of being residual means that this circulation along an absolutely continuous curve has to be zero. Okay. So it's maybe different from the Clark Jacobian, but it has to be close in this sense. Now that we have our generalized gradient, let's introduce a subclass of Lipschitz function, which admits such generalized gradient. So a function having a conservative gradient will be called path differentiable. Okay, so and it's a strict subclass of the class of Lipschitz functions. So now the question is, does it happen often? And we have nice sufficient conditions related to convexity. Okay, so the first three sufficient conditions are essentially related to convexity. So in the convex world, we have path differentiable functions. This is not enough to treat deep learning applications, and we need to resort to something else. So that's the fourth point. We introduce we don't introduce, but we consider semi-algebraic functions, or more generally definable functions. Semi-algebraic is already enough. And so what are those? This is a class of a special subclass of functions which has strong geometric and rigidity property. And it's possible to show that semi-algebraic functions are path differentiable. That's one of our results. And the good thing about semi-algebraic functions or definable functions is that they capture the vast majority of cases encountered in deep learning. So in other words, if you take your favorite deep learning application, there is a lot of chance that it falls, all the objects involved in the construction of this deep network fall in the category of semi-algebraic or definable functions. So it's a nice, well-behaved subclass which captures the vast majority of deep learning applications. All right. So now let's get back to backprop and our original question: what is non-smooth backpropagation? So we have our composition, and the only additional assumption that we will have is that we have Ji, a conservative Jacobian for each Gi. Okay, so for example, Ji could be the Clark subgradient if Gi is semi-algebraic. So we have seen that backpropagation computes a selection in the Jacobian product. And we know from conservative calculus that the product of the Jacobian is a conservative gradient. Okay, so backpropagation is a selection in this object, but what conservativity brings in addition is that this has the conservative gradient property. And so we have consequences of these results. So despite artifacts that we have mentioned in the introduction, it turns out that backpropagation is actually the true gradient almost everywhere. Okay, and this is a non-trivial fact. Okay, this is something that is often referred to in discussions about non-smooth deep learning, but it's not possible really to prove it without going through this conservativity property. We have other consequences. For example, we have a fundamental theorem of calculus for backpropagation. So we can circulate backpropagation along absolutely continuous paths, and it's compatible with these integral rules. And more generally, this provides a framework for a chain rule of backpropagation operation in a non-smooth world. Okay? And in particular, this allows to study training mechanisms for deep networks and robustness. So let's see training. Let's see examples of what could go on in terms of training algorithm. So that's an empirical risk minimization problem. I'm minimizing a finite sum, and I'm writing each element of the sum explicitly in the form of a composition. Okay, and so this is a way to model the fact that we are going to use non-smooth backpropagation. And this is typical in deep learning. Okay, so each element of the sum will be given in the form of a composition. You can think about layered compositional models in deep learning. We have an additional assumption. Each G have to be semi-algebraic with a semi-algebraic conservative Jacobian. Okay. We suppose that this is given. And again, as I mentioned, this is the case in virtually all deep learning applications. This can be extended to definability, but the semi-algebraic is already a large class. So what do we do with this? So the first step is to set for each I, di to be the product of those conservative Jacobians. And we know from conservative calculus that this will be a conservative gradient for the corresponding element Li. And once we have these, we average them. We get an object we call D, and D will be a conservative gradient for L. This is again application of the conservative calculus rules. Okay, so what would be the typical algorithm here implemented in deep learning libraries? It's a variation of the stochastic gradient algorithm with backpropagation in place of the subgradient or the gradient oracle. So we start with an initial guess, theta 0. We have step sizes which have to be positive, converge to 0, and be not summable. So this is a bit technical. And at each iteration, we pick up at random an index uniformly in one end, independently from the past, let's say. And we perform what is similar to a gradient step, but the only difference is that I replace the gradient oracle by the backpropagation operation. Okay, so I apply backpropagation to the loss related to the chosen index. So what does this? How does this work? Where these things are supposed to converge? That's the question that we want to tackle. Okay, so I just copy paste the algorithm here. It's a summary, the same as on the previous slide. We want to understand the asymptotics of theta k. So a few comments about this recursion. First, we know that backpropagation is actually an oracle for the D index ik for each iteration k. So that means that at each iteration, what we compute is an element of the corresponding conservative gradient. Furthermore, we may consider what is happening in expectation. Okay, so in expectation with respect to the random choice of the current index. So conditioning on the realization of the previous indices, the expectation with respect to the random choice of the current index is simply an element of the set valued field D that we have computed before. So again, D is the average of those DI. So in expectation, we compute an element of this thing. So what this means is that D, this conservative gradient, is the object which drives the dynamics. Okay, so the object which allows to study the dynamic is this one. And there is a famous work by Benaim of Bauer-Sorin. I mean, it is the continuation of a series of work on this approach, but they essentially did the non-smooth case. So they reduce the study of the asymptotic of this type of recursion to a study of differential inclusions. Okay, so time derivative of theta has to be an element of d theta. And on top of that, we have from conservativity that the loss function L, okay, so that's the original loss function that we want to minimize, will be Lyapunov for this differential inclusion. Okay, so using their results, we are able to analyze the asymptotics of this thing despite the artifacts, possible artifacts of the backpropagation operation. So the result can be stated like that. So I start with an initial guess. I assume that the step sizes are going to 0 fast enough. So that's not too fast, but fast enough. And I have this technical assumption. I need the sequence to be bounded almost surely. Okay, so I cannot do anything without bounded sequence. This is not completely satisfactory in terms of assumption, but yet it gives a result. So under those assumptions, the loss will be converging. So the loss will stabilize. And accumulation point will satisfy a notion of criticality. So they will be what we call decritical, meaning that 0 will be an element of this generalized gradient, conservative gradient. Okay, so this is satisfying. We have characterized the attractors of this backpropagation recursion. The question now is, as we have seen, there may be a lot of artifacts in this D, and in particular, there could be spurious critical points. Okay, and the question is, do those sequences converge to those spurious critical points often? And the answer is no, most of the time. Okay, and this can be more precisely stated as follows. So there exists a finite subset F. This will be the subset of forbidden step sizes. Okay, so I want my step sizes not to meet F, and this set is finite. And there will be a zero measure set N, and this will be the set of forbidden initialization. Okay, so and it has zero measure. And provided that those two conditions hold, the accumulation points will actually be critical in the usual sense. Okay, so meaning that there will be no artifact. I will only have the usual notion of criticality. 0 is an element of the Clark differential. Okay, so this essentially shows that backpropagation, despite its artifacts, has a minimizing behavior similar to what we would expect without the artifacts. So let's recap. We have seen that subgradients are not compatible with calculus, and as a consequence, non-smooth backpropagation may produce artifacts. We have introduced a notion of conservativity, which is compatible with calculus, meaning that performing non-smooth backpropagation with conservative objects will produce a conservative object. And as a consequence, we can interpret the backpropagation operation as a selection in conservative gradients. We have introduced this notion of conservative gradients. The consequence in terms of optimization algorithms is that combining non-smooth backpropagation with mini-batching, as is typically done in deep learning, will behave qualitatively similarly as in the smooth case, meaning that we are attracted by the set of critical points. We have ongoing extensions. I will not go into the details because I already talked for a long time. So I will finish my talk here and thank you for listening. And if there is any question, I can try to give answers.
So are there any questions? So would your approach also be able to probably even tell us why it is believed that when I do training with large batches, you seem to end up with sort of flatter optima? I mean, would one be able to sort of extend the kind of things that you are doing?
Okay, so that's a difficult question. So what we are doing is essentially a way to generalize the ideas that are valid in the differentiable world to the non-differentiable world. Okay, and so the answer I would say would be twofold. The first step would be to have an answer to the question that you ask in the differentiable world. Okay, because that would be easier. And if this is the case in the differentiable world, we could try to extend this to the non-differentiable world, eventually using those techniques. But I'm almost sure that if we are not able to prove such a conjecture in the differentiable world, we won't be able to prove it in in the non-differentiable world. However, that would be, I would use this technique if we had a proof in the differentiable world.
Yeah, because people are really interested in understanding. So I made a mistake there. It's not flat, but very deep minima. But when you do robust training, the kind of training that people do for adversarial robustness, they seem to be, I don't know whether people have actually tried to analyze it in the differentiable world also, but maybe something like this is probably what is happening. Maybe there are some, there is a notion of a conservative, perhaps a conservative Hessian also. I don't know whether all those make sense. Yeah,
that would make sense. That would make sense. It depends on the setting. So in some setting, it would make sense. In some setting, it would not. The issue will come if we try to differentiate discontinuous functions. So this could cause a lot of issues, and we have examples of problems that could occur. So differentiating Lipschitz function is fine, but differentiating discontinuous function could be very problematic. And actually, the second derivative of, so the ReLU function, the derivative is the step function, which derivative is 0 almost everywhere. So it's difficult to make sense of this.
Yeah. Any more questions? No. Then let's thank Vado.
Thank you very much.
Thank you, Edouard. Thank you very much. Bye.
Yeah.
Yep.
Hello. Did I lose you all? I mean, I'm a bit.
No, you're there. You're there.
There. Okay. Okay. Yeah. So our. Sorry, I have. One minute. I'm just sort of a bit lost. I've lost the program sheet that I had kept in front very carefully. Sorry about that. Oh, yeah, here it is. Yeah. The fourth speaker for today is Vianney Parche. Is that correct? Is that how you say it?
Yeah, more or less. Yeah.
Yeah, that's okay. Sorry, I've lost your. I kept your thing very carefully here. I'm sorry, I've lost your home page. I'm looking for it now, and I seem to have lost it also. So sorry, Nicholas, could you just jump in and give an introduction for him? I'm so sorry.
Sure.
Sorry.
Hi, Vianney. Thank you very much for coming to us from far, far away. Vianney is normally an ensayer in Paris. He works on game theory and machine learning, he's done lots of very interesting work. And today he's going to talk to us about this online matching in sparse random graphs.
Okay, thanks for the introduction. And maybe I just want to apologize if I look tired, because I'm actually in San Francisco right now, so it's more or less.
Oh my God.
Yeah, but it's a pleasure to be here. I'm happy to be a part of this France-India workshop. So
well, thank you for coming.
So I'm going to speak about this problem that we have. It's a paper with a student of mine and a postdoc on online matching in sparse random graph. And I really like this paper because this problem actually is a world class of problem, because it's motivated by a very practical motivation coming from the industry, from Cryo actually. And it's at the intersection of online algorithm, probability, learning, statistics. So I really like this problem. So without further ado, I'm going to describe the motivation and then give a mathematical formulation. Oops. Okay, so motivation is dynamic allocation of user to campaigns. So that's just the global motivation. I'm going to do some picture, and then I will put some math, but just try to keep in mind this picture because it might be helpful. So most of the current companies on the internet have this problem of trying to maximize the number of ads they display on websites. Okay, so that's the core business of Cryo, of Google, Facebook, Cryo, Amazon, all of those companies. And basically, what we have is that when you're running campaigns for companies, you are running the campaign simultaneously for several companies. So for instance, I can assume that my own company is running the 6 campaigns at the same time for Booking, Air France, Nike, Taco Bell, Porsche, and Louis Vuitton. And I have a bunch of users that will arrive during the day. The key thing is that some users are available to some campaign. So for instance, for the first user, this user, I can only show him a campaign for Booking or for Air France. And I cannot show him an ad for Nike or Taco Bell because he's not eligible. Okay, Nike does not want to display an ad for this guy. The second user, on the other hand, is only eligible for Air France and Nike, and so on and so forth. Okay, you get the picture. On the left part of this bipartite graph, we have the campaign, and on the right part of this bipartite graph, we have the user. And there is an age between a user and a campaign if I can display an ad for this user. Now, what I'm going to assume is, for this talk only, actually, because I can make things more general, but I will assume that I can only display one ad to one user because let's say he only visits a website once, and I have a budget of ads, and I can only display one ad of each campaign at most. Okay, so based on this graph here, what do we want to do? I want to maximize the number of ads that I can display. Okay, so that's actually finding a subset of ages such that each campaign belongs to at most one age, and each user belongs to at most one age of this subset. And my objective is to maximize the number of ages. So here in this specific example, it's easy to see that I can find a matching. So that's called a matching of size 6. I can match the 6 user to the 6 campaign if I'm smart enough. Okay, so here, if I was in this example, I will be able to say that I managed to display 6 ads and I'm happy about my algorithm. Okay, so that's what I've just described. This motivating example is nothing less, nothing more than what is called building a matching on graph. Okay, and for our purpose, we're going to work on random graphs, but for the moment, I can just define this on graphs. So again, let's go back to the modelization. So what is a graph? Graph, as you probably all know, is a set of vertices, V, and some edges between those vertices. Okay, so here I have 4 vertex and 4 edges. What is matching? A matching is a subset, as I told before, is a subset of those edges, such that each vertex of the graph is covered by at most once, meaning that each vertex belongs to at most one edge of my matching, of my subset that I picked. So for instance, for this graph, I have several matchings possible. The one on the left, bottom left here, basically is just picking the edge 2, 3. You can see that each vertex belongs to at most one edge. So that's a matching of size 1. And I have a better matching, better in the sense that here there are more edges on the right. And here this is the best matching actually. There are 2 edges. And each vertex belongs to one edge and only one edge. So here, this is the best matching possible in this graph. And the whole theory of matching and graph basically is trying to compute this matching given the graph, the matching with the highest coordinate in the graph. So that's the point. And if you remember correctly, I had a specific structure on graph. I had, as I told you, a bipartite graph. On the left side, I had campaign, and on the right side, I had user. So here, I'm going to consider in this talk only bipartite graph, where we have the set of vertices are decomposed in 2 sets, on the left part and the right part, U and V. And I have edges only between an edge on the left and a vertex, sorry, on the left and a vertex on the right. It's not possible to have an edge between 2 points on the left or an edge between 2 points on the right. Okay, and my objective basically is to maximize the number of find a matching in those type of graphs that maximize of maximal cardinality. And I will say that this matching is saturating if all the points on the left belongs to an edge. Okay, it might be the case that I have more V's than U's, and so that I cannot, of course, saturate V. But my point is to saturate U. Okay, so that's the global objective: finding a subset of edges, a matching that is of maximal cardinality, and hopefully of the same cardinality of U, the number of campaigns that I had before. That's my goal. And there are some theorem that tells you when this is possible. Okay, there's an old theorem which is almost 100 years ago, 100 years old, that tells you when this there exists a matching in a bipartite graph such that one side is saturated. I'm not really interested into this specific result, and because that's not actually the main concern of this presentation. Here, the motivation was assigning user to campaign. Okay, when I display ad, and there is a key feature that I did not mention yet, is that user, I don't know in advance all the users I will see during the day as company that is running the different campaign. Actually, what happens is at the very beginning, I have this bunch of campaigns that I'm running. So I'm running ad campaign for Booking, Air France, Nike, Taco Bell, Porsche, and Louis Vuitton, the same 6 as before. But I don't know yet the users I'm going to see. So what's going to happen actually is at the very I will have a first user that arrive on one website, and for this first user here, I will see that this user is only eligible for Booking or Air France because I have 2 edges, only those 2 edges, and then I have to decide if I'm going to display an ad, and if I'm going to display an ad, whether it's going to be for Booking or Air France. I have to make a decision, and this decision is made forever because I cannot go back in time and change my mind. So here, this first user arrived. I have to decide which ad I'm going to display. So let's say here I display for Booking. Good. The second user arrived. For this user, Air France and Nike are available. So I'm going to display an ad, let's say, for Air France. Then the third user arrived, and this user is only eligible for Air France. But here I have already depleted the budget of Air France, because I can only display one ad for Air France. So here you might say, well, actually, in real life, we can display more than one ad per campaign. This is true, but it's not really the issue. It can be generalized very, very easily. So here what happens is that this user, the third user, is only eligible to campaign Air France, which is already depleted. So I cannot display an ad for this user. Then the fourth user arrives. I can display an ad for this guy. Then the fifth user arrives. So I have the choice between Porsche and Louis Vuitton. Maybe I choose Porsche. And then the last one arrived, and I cannot, for this guy as well, I cannot display an ad. So here, what happens is that I have constructed a matching. It's still a subset of edges of this random graph, or random or not random, but it's a subset of edges of this graph, such that each vertex belongs to at most one edge. But here, instead of managing to match 6 users to 6 campaigns, I only manage, because I construct this matching sequentially in an online fashion, I only manage to match 4 people, 4 users and 4 campaigns. So I have a performance of 4 instead of 6, 2/3 of the optimal. So the point of online matching with a very long line of work is trying to find an algorithm such that that constructs sequentially a matching, as I did here, but in the best way possible. Okay, so that's the point. So just to formalize it, how does this work in this online matching in bipartite graph? I have those vertex U that are known here at the beginning. Those vertices are the campaigns. And what happens is that I have this latent graph here between U and V, but I don't know this graph beforehand. What's going to happen is I'm going to discover vertices of V1 after the other one. First, I will see V1 and all of these edge, then V2 and all of these edges, then V3 and so on and so forth. So at first time, I have my 3 in this graph here. I have the 3 vertices in U and only the first vertices in V that arrive, V1. This guy has 3 edges, so I can pick any one of them. Let's say I pick the second one. Why not? Then I have V2 that arrive. I have to pick an edges. Here, let's say it's the last one. And again, here I'm stuck because there is, once I've chosen these edges and that edges, 2 in red, I cannot pick an edges to which V3 belongs, and with the other vertex not already covered. So here in this example, again, I managed to match only 2 vertices on each side instead of 3. So that's the objective is to construct again an algorithm. So we want to construct an algorithm, a matching algorithm that does this construction sequentially, that with the highest possible matching size. Okay, so A of G is going to be the matching that I've credited on a graph G that I don't know in advance, and this quantity is the size of this matching. If I knew everything in advance, I will be able to pick somehow the highest, the largest matching, and this will be its size. Okay, the cardinality of M star of G, the optimal matching. And in this line of work, we measure the performance of an algorithm A by the competitive ratio, which is just the ratio between the size of the matching constructed divided by the size of the optimal matching. And I'm going to take this. I'm going to take the minimum over a graph, over a family of graphs. And this family of graph depends of the model I have in mind. Okay, so for instance, it can be any graph. So if this class of graph is any graph I want to consider, then it's what's called the adversarial case. If this class G is the class of any graph, but I assume that the order is random, so I can instead of saying that before V1, then V2, then V3, I just pick one of those vertex at random. I observe this one, and then I pick another one at random. I observe that one, and so on and so forth. So this is called the random order model. But the issue that we have is that for the application I had in mind, the add problem, none of those 2 classical settings are well adapted. The reason why, I mean, I'm not going to spend too much time on it, but the reason is that they are not creating sparse graphs, but rather dense graphs. And this does not really scale with the number of campaign and users that we have, that you have. So we needed something, we need a new model where basically I can add user in my graph if I want. Okay, so that the model is not constrained by the number of users I have. Okay, so we'll see later on how we can build this. So here I'm just going to describe the performance of the very naive algorithm that we call greedy. Greedy basically just say, well, if we don't know anything at any time, maybe the simplest thing we can do is just pick any edge at random. Okay, so you have a vertex that arrive, vertex VT that arrive. You have a bunch of admissible edge. That means UT. That means that UTVT is an edge, and UT is not already in an edge of your matching. And pick any one of them at random. So this seems quite natural, but actually we can prove, and I'm going to show it to you later on in a very simple example, that the competitive ratio of this algorithm is equal to 1/2, and this is the worst possible case. Okay, this is the worst possible algorithm, and actually there are better algorithms. There are algorithms that outperforms greedy and goes up to 1 minus 1 over E, which is, instead of being 0.5, is roughly 0.63. But our concern that we had, again, the criticism that we have about this kind of results is that this competitive ratio here, I'm going to see here in the next slide, of 1/2, which is the worst one, is when the world is on a pathological example, when for the worst case. And in real life, our point is that the world is not that adversarial. So the world has some structure. And the point that we want to do is we want to leverage the structures that we can see in the world to consider graphs, random graphs with some structure where the performance of greedy is going to be way better. So here is just the example on why greedy has a competitive ratio of just 1/2. Okay, so take the same kind of graph that we had before, but here assume that the number of campaign is huge, not just 3, but 3,000. And same thing for the set of user. It's also 3,000. And if you look at the first user, this user here, the user of the first half are going to be eligible for the campaign on horizontally here. So you have an horizontal edge. And this user here is eligible to all the campaign of the second half. And same thing for this guy, and same thing for this guy. On the other hand, on the second half, the user on the second half are only one edge horizontally. Okay, so here I can see that there is a very simple matching. Just I pick all the horizontal edges. And this matching is optimal, it's saturating, it's perfect. Okay, all users are matched to a campaign. But if I'm running a random algorithm greedy on this graph, basically what you're going to see is that the first user, the probability of picking this edge here is very small if I have many campaigns. So basically, this is not the matching I'm going to pick. The matching I'm going to pick is going to be more something like this. This user here is going to be matched to someone, to a campaign on the second half. Same thing for this guy here, second half, and so on and so forth. So basically, this is exactly what will happen. up to a very negligible number of you can compute it quite easily. Up to a negligible number of users, this is what's going to happen. And instead of matching everyone, if you just apply a naive random algorithm, you just match half of them, the first half.
I think you're muted. Suddenly.
I'm muted.
No, you're fine. We can hear you.
You're fine. Oh, I lost my connection. Sorry about that.
Okay, it's fine. Don't worry. If you have questions, feel free to interrupt, by the way. And so here, this shows that greedy has a competitive ratio of 1/2. That's the counter example, the worst case. And as you can see, this is a very pathological example. So our point was to say, well, if I'm going to look at real life graphs, they don't have this kind of structure. They have more structure. And we want to have, and they are sparse. So we want to build random graphs with structure that are sparse. And there is a way in probability to do that. And this is called the bipartite configuration model. So how does this work? So basically, it's a way of constructing a graph, random graph, either a random graph as follows. So here, remember, I want to build a bipartite graph between U and V, a set of vertices U and a set of vertices V. What I'm going to do is I'm going to decide beforehand the sequence of degrees of each vertices in U and the sequence of degrees of each vertices in V. And so obviously, if there's a constraint, is that the sum of the degree on the left has to be equal to the sum of the degree on the right. Okay, so I can pick two sequences here of degrees for U and V, assuming they have the same sum. And my point is, I'm going to try to build a random graph that respects this constraint. And there is a way to do that. And the way of doing this is just constructing for each point of U, di half edges, and same thing for V, and matching the half edge at random. So let's take an example. Let's say the sequence of vertex of degrees I want to build is for U 3, 2, 2, 1. You can see that U1 here has degree 3, U2 has degree 2, and U4 has degree 1. And for V, I'm going to build the degree sequence of 3, 3, 2. Obviously, the sum match, so I can find a graph that respects this. And the way of constructing this graph is at random. So I'm going to take V1. I take the first half edges of V1, and I'm going to match it at random with one of those guys, one of the half edges that goes out of U. So maybe this is this one. Then I'm going to take the second half edge that goes out of V1, and I'm going to match it at random with an half edge of U. Let's say it goes this one, and then I continue this process. So I pick someone at random, here I goes to V2, and so on and so forth. I pick an edge at random, and I'm going to build a graph like this. So this is the way this procedure creates a random graph that respects the degrees of U and V. Okay, here is the graph. The only issue, as you can see, is it might be the case that two vertices are linked by more than one edge. Here we have multiple edges between U1 and V1. But then that's okay, because what will happen is I will collapse those edges, and indeed I will not respect perfectly this sequence here, but up to a very negligible number of this sequence will be respected. Okay. So now that I know, if you give me a sequence of degree, I know how to build a graph that has almost this sequence of degree. And the bipartite configuration model consists in saying, well, I'm going to assume that each of those numbers here, D1, D2, D3, D4, are taken at random according to the same distribution. That's how you build a random graph, which looks like an interesting graph for us. So that's what we're going to do. We're going to choose a probability distribution over the degrees for U, the probability distribution over the degrees for V, such that if I have n vertex in U and t vertex in V, the sum of degrees is more or less respected. So I want that the expected number of alpha edges coming out of U is more or less equal, is actually equal in expectation to the number of edges coming to V. Okay, mu U is the expectation of pi U, and mu V is the expectation of pi V. So this is how I'm going to build my random graph. I have those two distributions. I'm going to pick a sequence of degrees for U and a sequence of degrees for V at random according to those distributions. And then I'm going to apply the procedure we've seen before. And this is what we call a configuration model. And if, as we said before, there are alpha edges that are not matches, because we don't have exactly equality between the sum of degree, I just discard every one, and I can discard as well multiple edge. That's not an issue. And that's what we're going to look at, the sparse random bipartite graph created by this probability distribution. And the question that we investigate is, can we control the performance of greedy, the simplest algorithm, in an expectation in such a random graph which have enough structure, more structure than the other side case? And the answer obviously is yes. We were able to do that. So how can you if you want to know we can analyze an algorithm in a random graph, there is something that is quite important, is that what you do not want to do is you don't want to pick a graph at random and then analyze your algorithm. What you want to do is build at the same time your graph and your algorithm. This is way easier. So for instance, here, what I'm going to do is I'm going to pick the sequence, the sequence of degrees of U. This is going to be fixed. And when a new vertex arrives, V1, I'm going to decide its degree at random, according to the probability distribution. And then I'm going to decide that if I take one, the first edges, and if this one is matched to U1 and this edge is available, this edge, the first one which is available, is going to be in my matching. The second one is matched to someone else, but obviously this one is not in my matching. And then I will have a second vertex that arrives, V2. Same thing, I'm constructing at the same time my algorithm and the graph. So here I have 3 edges. So the first one is going to maybe match this one. So this edge is not available because U1 is already taken. So I'm going to wait for the next edges if it's possible. So here I have built at random this edge between V2 and U2. This edge is available. Bam, I put it in my matching. And then the third one is map someone else and so forth. So here what is really important is that I'm building at the same time my graph and my algorithm. Okay, that's how you can analyze algorithm in random graphs. And if you do that, and you're cautious enough, you can see that the if we call M of S, this is the matching that we have after seeing a proportion S of vertices of V. So M, the final matching that we have is M1, and at the beginning we have M0. So M, and if the number of vertices that we have is big enough, you can see that M of S is going to be more or less continuous. And actually what we can prove is that this function here, M of S, converge with in probability, and actually almost with very high probability, exponentially fast probability. This function here, M of S, which is the size of the matching that Greedy creates on a random graph created by configuration model, converge with high probability there towards the solution. This function here, 1 minus phi of U, where phi is a genetic function, genetic series of 1 with G of S, where G of S has an explicit form. Well, actually has a form given by this ODE. What we prove is that if you're giving me the distribution pi U and pi V of the degrees, then I can compute a genetic series phi U and phi S. I can solve this linear this ODE, this PDE here. So this gives me G of S, and then I claim. But we proved, it's not a claim, it's a proof. So we prove that the size of matching that we construct closely converge to this deterministic equation. And then we run a simulation, actually, obviously, because it's a theorem, so it's true. But we can show that this converge quite quickly, more quickly than what we are able to prove. But still, it converges. So it's a better news than what we have. And yeah, our model at the end, so that's perfect because that was kind of the end of the talk, so it's perfect. Here, as you can see, we have only bounds as n goes to infinity, so asymptotic bounds in probability, but we can have non-asymptotic bounds. We have exactly the same thing. We can control the deviation, and they are very, very small. And as I said before, I assume that each campaign has only one budget, but I can put a budget of only one ad, but I can put bigger budget, and I could do more and more and more stuff. And that's why we have this paper. It's going to be presented at NeurIPS in a few weeks. I'm not going to spend too much time on the proof because we don't have time. So here there's some simulations showing that that's our that what I said before, the empirical results are very close to the theoretical one, but that's it. And I'm right on time, so I just want to thank you. And if you have any question, feel free to ask them now or contact me later on. I will be happy to answer them.
There is a question in the chat. So Purushottam, maybe you should just ask the question. And thank you, Vianney.
Okay, so you want me to read the question? Is that correct?
Or maybe Purushottam, you can just say your question.
I would love to. Thanks, Vianney, for the nice talk. So the first question I had was, I think, a very straightforward one. Whether this approach will extend if the edges have weights on them or not.
Say again?
Whether this approach will extend to graphs where the edges are weighted.
Yes, yeah, we can do it with weight on edges. Yeah, totally. Actually, it's if you put the weight at random, then you can do things like this. Yeah. So it's not really an issue, those weights. Here you're right. Actually, here we just say that each ad has the same value, but typically they do have different values, and you want to pick the highest one.
Right. So thanks, Vianney. The second question I had was, maybe I'm reading too much into this example you took, but
Yeah.
usually advertisers would probably want to reach out to more than just one
Exactly.
audience member.
So
Does
here,
having that relaxation make things easier for the algorithm?
no. So here actually is just for the sake of pronunciation. But here, if you assume that a campaign has a budget size, so you say here instead of 100. So there's two ways of doing this. There is a very ugly way that consists in duplicating 100th time the campaigns that you have. So this is very ugly. And the other and actually there is some issues with correlation. But the other way is just saying, well, our analysis actually can be extended to the case where we have more than one user per campaign. But then instead of having the ODE that we have to solve is more complicated. But it works the same way. It's the same proof, same technique of proof, and it's the same idea.
Thanks, Vianney. That answers my question. Thanks.
Any more questions? Let's thank Vianney. Yeah, sorry to keep you up so late in the night. Or so early in the morning.
Yeah. Or so early in the morning, I think. Yeah.
Actually, it's late.
Yeah.
Okay. Thank you, Vianney. Yeah. Thanks for
About
great talk.
2:30, I think. Yeah. Yeah.
Thanks.
Okay. Thanks.
Bye-bye.
Bye.
Bye. I'm going to review. I'm sorry.
Yeah. Okay. So so the next speaker for today is Aurélien Bellet. And so Aurélien will be telling us about federated learning, advanced and open challenges. And I'll give you a brief bio of Aurélien. So currently he's at University of Lille. He's also an invited professor at Telecom Paris. His interests are primarily in algorithms of machine learning, large-scale algorithms, which good trade-offs, that's what he says. Yeah, in his web page. Yeah. So Aurélien, the floor is yours.
Hello, everyone. I hope you can hear me, see me.
Yeah.
Yeah, great. Let me try to first share my slides. Yep. Okay, that's the end, but let's go back to the...
Yep, it's there.
Yeah. It's there. Okay, great. Thanks a lot for the introduction and the invitation. So I'm a researcher. So my main institution is actually INRIA. So I'm a researcher there, like a French kind of research institute for CS and applied math. But yes, I'm also associated with the University of Lille and a bit with Telecom Paris. And so I work on machine learning and more specifically these last couple of years, kind of these, let's say, federated, privacy-preserving machine learning settings, where the idea is that you want to learn from data that is not accessible in a centralized place, but instead is decentralized, possibly because this data is collected by different entities. And you don't want or you cannot just put it in the same place and centralize it, because maybe the data is too big, it's too costly, or the data is too sensitive. It has kind of privacy constraints. Okay, and so my talk is going to be kind of mostly a bit of a, let's say, tutorial talk about these topics of federated learning, and I will also touch upon, of course, some of my recent work in this direction. But really, I wanted to kind of give a little bit of overview of the topic and what are the current kind of challenges, because this is a relatively new topic, and so I think it's worth kind of introducing it. All right, great. So this is the outline. So first, I will try to give a little bit of a high-level view of what is federated learning and why it might be interested. I will then present, let's say, a baseline algorithm for federated learning, which is kind of simple to understand, but of course, kind of doesn't solve all problems. And then I will spend some time essentially discussing three I think what are three of the main challenges that remain kind of a little bit also open in federated learning, and also describe briefly some some recent work to try to tackle these challenges. Okay. All right. So what are we talking about first? So we want to do machine learning, and of course the input to machine learning is data. And typically the standard setting that is considered in machine learning is to consider that this training data is essentially accessible in a centralized place, right? So the simplest setting would be you are working on one machine like your laptop, and the data is on the hard drive of the laptop. Okay, but more generally, okay, the data might be bigger, and you might want to kind of store it or distribute it in a cluster or data center. So I still call this centralized in the sense that you have kind of easy and efficient access, unrestricted access to the data, which is all in the same place, some kind of server. Unfortunately, this is not really how the real world data is located in many applications. Or at least to start with, this data is typically decentralized. So because it is generated or collected by different entities, you can think of different hospitals for patient data. You can think of different kind of client data collected by different companies or different public institutions, and of course, different kind of personal devices that people may be using, which collect kind of their personal data, essentially, right? And so there is a bit of a dichotomy here between how we typically do machine learning, which is centralized, and kind of where the data really is in practical use cases. And so, of course, the typical way to resolve this problem is to essentially share this data, centralize this data, but put it in the right place, in the same place. The problem is that we don't always want to do that, or sometimes we actually cannot do that. So there are two main reasons here why we may not want to centralize the data. The first one is when this data is big, it may be generated continuously, and it may be too costly to just transfer it to a server. Okay, so there are applications like self-driving cars, for instance, which are expected to generate gigantic amounts of data kind of every day, all the time. And so this will probably not be a very efficient solution to have to transmit all this data. And then there are other kind of applications where maybe the data is not that large, but it lies on some wireless devices which have limited bandwidth, limited power. And so again, transmitting data frequently is not really an option. And there is a second motivation or a second case where you cannot centralize data or don't want centralized data, which is something that I'm really interested about, is when the data is considered to be too sensitive to be shared, essentially, right? And so here you can think, of course, of personal data, for which there is kind of growing public awareness in many countries of kind of users don't want to trust some service provider with sensitive personal data. There is also increasing regulations on data privacy. So in the EU, there is, of course, the GDPR, which kind of puts restrictions on which data can be collected, what kind of data can be processed, and how. And there are other contexts also where data may be considered sensitive. It is in situations where essentially when different entities want to keep control of the data because it gives them a competitive advantage. So this can happen, of course, in kind of business use cases. For example, some companies might be willing to collaborate to learn something interesting about their joint data, let's say client data, but they don't want to, of course, reveal the identity of their clients to others. This happens also in research, notably in medical research, where kind of keeping control of the data, collecting some data, curating some data represents kind of a competitive advantage for publishing. Okay, so researchers in such domains may not be always kind of very willing to give away this data so that it's put in a central place. Of course, there is another thing what could think about doing is to say, okay, there is this data decentralized everywhere. I'm just going to learn locally on the local data. Okay, so kind of each entity will learn on its local data set. So of course, this has other problems. Typically, this local data will be small, and so you will have problems like overfitting, right, which will make the model that you train on this data not generalize very well to new points. Or again, in kind of more, let's say, medical studies where the model is used not so much for predicting on new points, but more to do a conclusion about a particular phenomenon, like whether this variable has a significant effect on this disease or something like that, then you might just get non-statistically significant results. Okay, and so basically you don't have enough data to conclude. Another problem is that this local data set may be biased in the sense that it may not be representative of the target kind of distribution or population that you are aiming at. So again, to continue on this kind of hospital example, each hospital see a different kind of population of patients. They have also slightly different ways of taking care of the patients and so on. And so whatever you learn on one hospital might not generalize very well to other hospitals. All right, and so federative learning is really the goal is essentially to reconcile those two aspects, to be able to learn from the whole data, to train machine learning models on the whole data, but keeping this data decentralized. Okay, and so it is more of a collaborative process where instead of sharing the data itself, you will share kind of the exploitation of the data. Okay, so this is a relatively new topic. So when I started working on this around, let's say, 2016, this was kind of emerging and not so many people working on it. Now it is very booming. So in the first half of 2020, there was like more than 1,000 papers, for instance, published there. Okay, of course, not all of them are good, but it kind of gives an idea of how this thing has been growing in the past couple of years. We are seeing also first kind of real-world deployments by several companies and by also researchers. Some kind of salient aspect, I think, of federative learning is that it is quite highly multidisciplinary. So it involves, of course, machine learning and optimization, but it also involves privacy and security, kind of networks and systems issue, and so on. So it requires kind of, it is at the crossroads of different kinds of expertise. And okay, if you think about a little bit what could be the future of federative learning in a kind of ideal world, if we solve all challenges, then maybe we could think about quite nice things, like maybe being able to do remote data science, right? So be able to analyze data that we're not able to see and that sits, we don't necessarily even know where exactly, but we can enable kind of the whole pipeline of exploring the data and generating insights from data without actually having access to the data. I think this is also kind of promising way to potentially make machine learning and AI kind of more accessible to citizens so that they can themselves define kind of the usage and the tasks that they would like to use their data for in a kind of collaborative manner instead of kind of just having to follow maybe the usage that are pushed by some big actors like big tech companies. All right, so this would be kind of a bit the vision for the future, but of course we're not there yet, but we already know kind of how to do some things. And so to illustrate that, I will now go a little bit more in detail and show you what a concrete kind of federative learning algorithm looks like. So let me introduce now a few notations. So we're going to consider a set of K parties. So those are the participants to the federative learning process. So you could imagine that there are hospitals, for instance. And then each party K holds a data set. Okay, so I'm going to denote that dk. It has nk points. Okay, not all participants have the same number of data points necessarily. And I will just denote by n kind of the combined size of all local data sets across all parties. I will be considering throughout this talk kind of empirical risk minimization settings where we essentially decide on a family of models like linear models or a particular architecture of neural network with parameters. And we're going to try to fit the parameters. And so I will denote these parameters by theta. And the problem we will formulate as very standard in machine learning as essentially empirical risk minimization. So you want to find the parameter theta that minimize the overall prediction error, the overall loss over the whole data. And so in the case of federative learning, we can essentially separate this into K terms, where each loss function here computes how good the model with parameter theta is to kind of model the data of party K. Okay, and we typically put some weights on this loss function to give more weight to participants that have more data. All right. So this is the standard setup, and then this is a kind of essentially a baseline algorithm, which is the standard algorithm right now for federative learning, which is called federative averaging, and is essentially some kind of local SGD approach. If you have heard this term local SGD before. So it goes as follows. On the left, I have this kind of high-level figure, which shows the process, and on the right, I will try to highlight in the pseudocode, okay, the parts, okay. So this algorithm relies on a server, which doesn't hold any data, doesn't receive any data, but essentially helps to coordinate the process. And so here we have 4 parties with their local data. So the first step of the algorithm is typically everybody agreeing on, the kind of data that will be used and the kind of model that will be trained. Let's say here some kind of small neural net, and there is some initialization, right? So that everybody starts with the same model. And then the training algorithm will essentially proceed in rounds. That will alternate between local learning steps and aggregation steps. So at each round, first, each participant will essentially update the local model on its local data. So this typically in practice is done with gradient descent methods, right? So you can think of doing local SGD steps. So typically assume that this loss function is differentiable in the parameters, and so we can compute a gradient, which gives us roughly a direction for which to change the parameters in a way that this will make the model better on the local data. And so we can do several local steps of this, right? So here the number of local steps is L. And so this happens on the participants essentially in parallel. Everybody updates the model to make it better locally. And then there is an aggregation step where these local updates are shared, in this case here with the server, so that they can be aggregated. And essentially they are aggregated here, as you can see on the right, as some kind of weighted average, okay, because we had weights in the objective function. And this creates a new global version of the model that can be sent back to the parties, and we iterate on this process, okay, until convergence, typically. All right, so it's kind of intuitive and simple. Of course, this will work in some cases and not work so well in some other cases, and there are also other challenges in federative learning that essentially cannot be addressed with this simple baseline algorithm. And so I will now review a little bit the kind of challenges that right now the community is trying to work on. So the first one that I want to emphasize is how to deal with heterogeneous data. So the idea here is that so federative learning maybe at first sight might look similar to kind of doing distributed machine learning on a cluster. These kind of distributed ML algorithms, that are designed to essentially learn faster by distributed data and computation across different machines. But the main difference with this here, of course, is that we don't decide how the data is distributed across the different participants, right? In particular, these local data distributions, they may be arbitrarily different, which makes a lot of sense because essentially this reflects kind of the production patterns and usage of the particular entity that is collecting or generating the data, right? And so you can expect that the data distributions across parties will be quite different, so quite heterogeneous. And then you have a problem with the previous algorithm in particular, which can essentially suffer from local drift, okay? So which is kind of depicted in this figure. This is the idea that if you do too many local steps, too many local gradient steps, but the data is quite heterogeneous, then each client will be kind of pushing the model parameters in different directions. And then when you do the aggregation step, you might essentially end up going in a direction that is more towards the average of the client local optima than the actual global true optima, okay, which would be here in blue. Okay, and so this creates challenges because, of course, you can remove this problem if you synchronize or aggregate after each local gradient step, but then you need to communicate a lot, right? And so there is quite a challenge here in how to design algorithms that minimize communication costs. For example, we minimize the number of communication rounds. And more generally, this kind of heterogeneous data a little bit is at odds with maybe learning a global model, or at least it raises the question of whether the model that we will learn, the global model that we get in the end, will actually be useful to all the participants, or maybe it will mostly be useful to the average participant, or participants that are more like the average. And maybe some of the participants will get a model that doesn't work for them, right? So these are kind of the kind of challenges raised by heterogeneous data. And so one way to address that, which I've worked on quite a bit, is essentially in learning personalized models. So the idea is to say, okay, if data is heterogeneous, maybe training a single global model is not a good idea. Instead, let's try to learn a model for each participant, but doing in a collaborative manner, sharing kind of information across participants, so we can learn something better than, of course, what each participant could learn on its own. So one possible way to formulate this is what we did in a series of work where essentially we were inspired by multitask learning, kind of seeing each participant as a machine learning task in itself, but making an assumption that these tasks are probably related, right? And that there are users that have similar data distributions because they have similar behavior, for instance, or they have similar taste. And so you can expect that there should be some way to share information across users to improve things, okay? And so the way we formulate this is essentially by learning models specifically for each user, okay? So now we don't have a single model theta, but we have theta 1 to theta k. And we try to find here in the first term in the objective function model theta k, which is good for the data of user k. Okay, so now we have personalized models, but of course we don't want to only have this in the objective, otherwise it's just equivalent to everybody learning on its own data in isolation. And so what we add is essentially a term which essentially captures the fact that there is some users that are more similar to others, which is captured by this weight between user k and user l, and the higher this weight, the more similar the two users are. And in this case, we want the model parameters of those two users to be similar. Okay, so essentially, user with similar objectives should have similar models, which is a way to share this information and get models that generalize better. And the idea is that we optimize essentially both the personalized models and the similarity weights jointly. Okay, so we learn both at the same time. So this works quite nicely in practice. We also investigated recently some other ways of thinking about this personalization in fidelity learning. So one other possible way is to make kind of statistical assumptions about how the local distributions kind of relate to each other. And so in that work, which is going to appear at NeurIPS actually this year, is a case where we make what is, I think, a natural assumption, which is to say that there is a number of underlying distributions, and then each local distribution, data distribution of a participant is drawn from a mixture of these distributions, right? So in other words, each local distribution is some kind of weighted combination of a small set of underlying distributions, and then you can design fidelity algorithms that look a little bit like expectation maximization, where you learn the parameters for these underlying distributions, and also each participant learns personalized weights that it puts on this distribution. All right, so essentially this idea of learning personalized model is now getting a very popular way of trying to address this problem of heterogeneous data. The second challenge associated with fidelity learning is about privacy. So how do we protect privacy in the context of fidelity learning? So one might think that because we are not sharing data, okay, in the algorithms that I presented, we are never sharing the data, but we are sharing parameters of models that are, of course, computed on data. And unfortunately, this is not enough. So not sharing data is not enough to guarantee kind of robust kind of privacy guarantees. And we know that because already in a more centralized setting, we know that machine learning models are susceptible to attacks on data privacy. Even for an attacker that would have only access to just the trained model. So it sees no data, nothing, only the final model that is trained. And there are quite significant literature now on such attacks, things like membership inference attack, where essentially from a trained model, you want to infer whether a particular individual, a particular data point that you know was in the training set or not. So it turns out you can do that with quite good performance in some cases by, for instance, exploiting the fact that the model will tend to be more confident on points that it has seen in training than on new points. And you can go even beyond that. You can in some cases reconstruct actual training points that were used to train the model just from the model itself. Okay, and so I worked a bit recently on that in the context of genome-wide association studies, where in some cases you can really reconstruct the genome of specific people that were in the dataset only from this kind of linear model. Okay, so of course reconstructing the genome of someone from a model sounds quite bad, and so we would like to avoid that. And again, this already happens if you only see the final model, but in federative learning, in a way, you are offering an additional attack surface, at least you can argue so, because the server in the algorithm that I presented before, or the participants, they will not only observe the final model, but they will also observe intermediate model updates, okay, some kind of sequence of updates from different parties. And so in a way, we are offering even more surface for an attack. You can expect that you can actually learn more things about the data in this setup. And so we need to protect against that if we want to have kind of rigorous privacy guarantees. And of course, this requires to define a little bit more formally what it means for an algorithm to be private. And so typically in machine learning and now also many other fields, the mathematical definition of privacy that is kind of the standard is known as differential privacy. So I'm not sure to which extent people in the audience are familiar with it, but I will anyway here give a kind of intuitive view of what it requires. Okay, so differential privacy is a property of an algorithm. In particular, it's a property of randomized algorithms. And so an algorithm in the context of data analysis or machine learning takes as input some data points, okay, x1 through xn, and outputs essentially some element in an output set, but essentially this output is random. Okay, so you can see the output of this algorithm as a random variable, which has some distribution over the output space. And of course, in the context of machine learning, the output space here could be the space of parameters. Okay, and the algorithm would be a training algorithm. So now what differential privacy requires, or the way it defines that an algorithm is private, is to say that if I apply my algorithm to a data set here, the blue one, or the one that has this blue point, or if I apply it to the same data set where I have replaced one data point by another, then the distribution of the possible outputs when I apply the algorithm on the first data set D or on the second data set G prime should be similar enough, close enough. Okay, and how to measure this closeness typically is some kind of essentially requires that the ratio between the probability of observing any possible output in either case is bounded. Okay, so it is not much more likely to see a particular output if the blue point was in the dataset or the red point was in the dataset. All right. So a little bit more formally here, you can say that an algorithm A is epsilon differentially private, DP, if for all such neighboring datasets, D and G prime that differ in only one point, and all possible sets of output, then essentially the ratio of the probabilities that A of D is in S and the probability of A of G prime is in S should be bounded, and essentially this parameter epsilon bounds the log ratio of these two probabilities. Okay. Good. So this is a very useful definition. In many regards, it has many desirable properties that allow us to work with it in practice and design algorithms that satisfy this definition. So to see how this can maybe be used for federative learning, let's look a little bit at how a typical federative learning algorithm looks like, including the one I presented. Essentially, the only place where the participants interact or exchange information is when we do this aggregation step, right? Where so the participants compute some model update locally, and then they exchange or they share this model update so that it can be aggregated by the server. Okay, so in the simplest case, just compute an average, which is then sent back to the participants. Okay, so in fact, this is the main step that we need to make private. If we're able to privatize this step, then we essentially have private algorithms. So how to do that? So you can think of different settings. So maybe as a warm-up, you can think of differential privacy in a centralized setting where maybe the server will be trusted to collect the raw updates. And so in this case, the server, what it would do in this case is compute the true average and then add some noise to it. Okay, typically in differential privacy, we use often Gaussian noise or Laplace noise. And then it will reveal the noisy average. Okay, and we can show that this satisfies differential privacy for the parameters that you want if you use noise that has sufficient variance, which is a function of the privacy parameters. Unfortunately, we don't want to trust the server again. We want to be in a case where the participants don't want to trust others with their private data. And so the model updates that might reveal something about their data. And so typically what you would need to do then is that each participant, before sharing its local update, you will need to locally randomize it, add some noise to it before sharing it. Okay, and then the server will collect these noisy updates and average them. All right, so the problem now is that, as you can probably a little bit guess intuitively, is that the amount of noise that you have to add in the end in the second case, where each party needs to individually hide its local update to the server, is much higher than in the centralized case, where the server is allowed to collect the raw updates and only add noise to the average to make the average differentiate private. Okay, and so the error in a way due to privacy becomes much larger. In the second case, typically it is a order magnitude square root k larger when k is the number of participants. So if you have data that is massively distributed, then there is a huge gap, and so you might not get a very reliable result when you compute this average, which corresponds to the aggregated model. Okay, so there is really, with differential privacy, this privacy utility trade-off. If I want more privacy, I need to pay more utility, but this thing can be optimized in some way. And so this is a challenge that, a very important challenge in federative learning, is to make this privacy utility trade-off as good as possible while maintaining computational efficiency, because improving this privacy utility trade-off might also require the use of some techniques that are computationally expensive. So, in fact, one way to do that is to rely on cryptographic primitives, secure multi-party computation primitives, to improve this trade-off. But again, this can be quite expensive. And so here I'm going to present a recent contribution where we give a very simple protocol for doing this differentially private aggregation step with a better privacy utility trade-off, which relies on adding essentially users securely exchanging pairwise noise in complement to the independent noise that they add to their own value. Okay, so the algorithm is kind of simple. It works like this. So there are a bunch of users that will exchange correlated Gaussian noise with each other. And so this noise is here Gaussian with some variance. And then, okay, the two participants will agree on this noise, and one will add it, the other one will subtract it. Then each participant independently draws some noise that it doesn't share with anyone, again, Gaussian with a different variance. And then each party reveals or shares with the server the sum of his private model update, the sum of this pairwise noise, and this independent noise as well. Okay, so now the server receives something that is the sum of a bunch of things, the true value, but also some noise terms. Some of them are correlated with others. Okay, and so the idea here is that now if you average all these contributions by the users, all those noisy contributions, all the pairwise noise terms will actually disappear because they cancel each other pairwise. And you will only be left with essentially the independent noise. And we can see that we can scale this noise so as to match the best possible privacy utility trade-off, which is the one of centralized settings. So if the server was trusted to see the raw model updates. Okay, so this pairwise noise essentially allows us to recover the best privacy utility trade-off. It is also scalable. So what we show in the paper is that it is sufficient for each party to communicate with essentially log k other users. Okay, so even if I have thousands or even millions of users, each participant doesn't have to communicate with that many other people. So this preserves scalability, and we show this is also robust to some collusions. So if the server colludes with a subset of the other participants, we can still get guarantees, and we can even sustain other kind of problems like a user dropping out in the middle of the protocol, or even malicious behavior by the users. So we can make this protocol kind of verifiable, so that it is not possible to cheat, to lie about the values without being detected. All right, the last challenge that I want to briefly mention is kind of related to putting this federated learning technology to practice. There are many challenges associated to this when you want to deploy these things in production systems. So typically there are technological challenges like trying to develop general purpose software libraries, which can be easily deployed given constraints that you find in production systems, and the fact that you have to make different production systems talk to each other, right? Because they typically belong to different entities. There are also, of course, very important regulatory or legal challenges with questions such like when should model updates be considered as personal data, or when can we just consider them as non-identifiable data anymore, and how to more generally ensure compliance with current regulation, for instance, GDPR. And then there are questions a little bit more towards the stakeholders, right? How to convince them that federated learning is useful or will bring some benefits for them, and how to make this process as transparent as possible to the end user, so that to them it is almost the same as if the data was centralized. So to explore this, I have recently started some collaborations with some hospitals, in particular the University Hospital of Lille. And so we are exploring these questions in the context of a project that we have with them. So we have started developing our own kind of code base to be able to adapt to the constraints of the hospital systems. And we will soon be deploying a proof of concept across, in this case, a small number of French hospitals, 4 to start with, but it turns out it's complicated enough for many reasons to do these deployments already on 4 hospitals because of these more kind of practical problems that we need to face. And we are planning very soon some deployments and concrete tasks with real medical data, which requires, of course, to have answers to this kind of legal or regulatory questions that we have. And so for this, we have some official support from the CNIL, which is the French Data Protection Authority, which helps us, essentially helps us on these legal aspects, things like writing data protection impact assessments and so on. All right, this kind of concludes my talk on federated learning, and I will end with a little bit of advertisement, actually, if you're interested in keeping up with the advances in federated learning, which is not that easy, again, because there are so many papers that come out. I had the chance to participate in a very wide survey paper, which has been published in Foundations and Trends in Machine Learning, which was really collaborative effort. Like there is more than 50 authors that collaborated on this paper. So I think this is a really nice place to start. And then I am also co-organizing an online seminar on federated learning, which has weekly talks, usually on Wednesdays, 1 p.m. UTC, that cover all aspects of federated learning. And even if you cannot attend the talks in live, we put all videos and slides of the talks online. So all the previous talks are online. So if you want to binge watch some federated learning talks, you can. That's it from me. Thanks a lot. Happy to take questions.
Nice. Yeah, I think binge watching federated learning sounds really. Yeah. Any questions for?
Yeah, I guess I have a question. I don't see any right now in the chat. Aurélien, thanks for the nice talk.
Very nice.
And please say hello to Pascal Denis for me.
Oh, sure, I will.
But the question is, it's more about about these attacks on the systems. I don't really, I haven't really kept up with this. We have a similar problem that we'll probably talk about tomorrow when we talk about explainability, because the more interpretable our machine learning systems become, the more open they are also to attacks and sort of subversions of differential privacy. But I mean, for sort of state-of-the-art systems, how bad are these attacks? I mean, are they really? I mean, are there sort of empirical gauges or studies that show that we really are in trouble with this, or is it more of a theoretical worry? That's I don't know. I think with the interpretability, we're so much in our infancy with the interpretability, say, of deep learning systems that we can't interpret them, so we're not opening them up to differential privacy attack any more than they were beforehand.
Right.
But
yeah, so this is a very good question. So unfortunately, at least I think when it comes to at least some specific applications of even centralized machine learning, but more generally federated learning, these attacks are quite real. So I mean, some of these papers that are cited here, they show concrete attacks, which sometimes require a bit of kind of auxiliary knowledge from the attacker, but sometimes not that much. And in federated learning, you can even mount attacks that kind of are a little bit more malicious. So when the attacker might not be just a passive attacker, but because it participates to the training algorithm, it can actually act in a way to even get more information. And so there are works, for instance, recent work that shows how you can try to reconstruct kind of input data from model updates when you train deep neural networks, and even in the passive setting under some situations. But then if the adversary is even active, so it can even inject some data or inject some layers somewhere well designed and so on, then this can become even completely catastrophic.
Right. Oh yeah.
Failures.
That's a good point. That's a good point, Alvin. Yeah, I hadn't thought of that. And that connects up with Purushottam's talk on, and maybe Purushottam, you can come back with your question, which probably isn't silly.
Well, I thought it was a bit silly. So the question is mostly about nomenclature. So when I used to be a student a decade or so ago, we had this term called distributed learning. So is federated learning a distinct paradigm for some additional features or some other considerations, or is it exchangeable in terms of terminology with distributed learning?
Yeah, this is a very good question. So I tried to say a few words at some point on that here, but maybe I wasn't very clear. And this also is way more, I think, general than just this one point, right? But in general, with this, maybe you will need to define more specifically what you mean by distributed machine learning. But in many cases, in most cases, this distributed machine learning aims at kind of training faster by kind of distributing the computation, right? And so, for example, in a cluster or in a data center kind of situation. And so in this case, one major difference with federated learning is that you have access to the entire data set, or you can choose how it is distributed across essentially the machines. And so typically what you would do is distribute this in a very uniform way, right? Because this is the best thing to do. If all the data sets locally on each machine look similar enough, you can expect that you can do much more parallelization, much less communication, because you can do more work locally and synchronize not so often. And so the one big difference in federated learning is that the data comes in a distributed way, in a way that you cannot choose it, because essentially it is how the data is at the beginning, kind of collected by different parties. And so this creates situations where the different local data sets can be very, very different, very heterogeneous, both in size and in distribution. Okay, so this is, I think, one key difference. There are, I think, many other key differences. So the fact that you want to preserve privacy, I think, is also kind of a bit more specific to federated learning, at least, again, if distributed machine learning means learning faster, then typically, I mean, you have access again to the data, so there are no really privacy issues during training. And then there are other things in terms of algorithm design, the fact that these participants that hold the data are actually potentially user device. They might not be very reliable. They might not always be available all the time. So the kind of updates that you get might come from clients that are not always the same. Maybe who shows up at which time step is kind of not uniform and very correlated to, I don't know, different time zones, you know, users having their smartphone kind of plugged in or not during the night, you know. And so all sorts of these kind of constraints that come from the fact that you are really learning from user data and not data that you have yourself distributed uniformly makes a lot of difference in how typical algorithms can perform and how you will design algorithms that can perform better.
Thanks, Aurelie. That was really eye-opening. Like this seems to that federated learning is clearly a distinct paradigm. It clearly opens up other issues that distributed learning never had to face.
Exactly. At the same time, of course, there is a lot to borrow from this distributed machine learning literature. And of course, I mean, if you think about the simple algorithm that I presented here for this federated averaging algorithm, it looks quite similar to maybe some distributed machine learning algorithm, again, which is the reason also why it has some problems on heterogeneous data. But of course, federated learning literature borrows definitely some ideas from this kind of older distributed ML topic. Yes.
Any more questions?
One more question from Mohammed. Mohammed, maybe you can.
Oh, hi. I was wondering about the attack assumptions that you consider against the efficiency, I mean, of the differential privacy techniques. Usually these assumptions are based on the fact that they target only single node or minimum number of nodes or the global server.
That's a good question. So here I mentioned only kind of privacy attacks. There are also other kind of attacks, of course, that you can try to inject backdoors or, you know, poison the model so that it predicts something that you want on particular kind of data and so on, right? So these are also interesting problems actually that I haven't mentioned here. They are not really about privacy, but they are about, you know, making sure that we learn the right thing and there is no problem with the model we learn. In terms of the privacy attacks, yes, typically they will target a particular user. So you're trying to typically you're trying to infer some information about either specific points of a user dataset or some general information about the local dataset of one user in general, right? And so there are in fact also differential privacy guarantees. You can define them in these two regimes. You can design a differential private algorithm that aims to hide the presence of a single data point, or stronger, that aims to hide the presence of an entire user participating to the training. And so you can consider both problems. Of course, it is harder to hide, or let's say it has a higher cost in utility to hide the presence of an entire user in the systems, in the sense of differential privacy.
Are there some works, I mean, current works about the notion of federated attack strategy or something like this in the context of federated machine learning?
Mm-hmm.
So just a question, I mean, if you are aware of this kind of work.
Yes, so this, I don't know, the name doesn't suggest something very specific. So, but let's say the last paper that I cite on this slide, or there are also a few more recently, really are, yes, about designing attacks that are specific to the federated learning setting. So that will target some, let's say, some specific model updates or sequence of model updates by a participant and try to infer sensitive information about its data, such as reconstructing its data. So a number of papers have studied that and showed that this is possible in some cases. I can share more references if you like. You can drop me an email if you're looking for references on that. But this is quite a recent topic, so I think there is still a lot of room to design better attack specifically for federated learning setting that exploit this time dependency, this sequentiality of observing several model updates by the same client.
Okay, thanks very much.
No more questions. So let's thank Orlean for.
Thanks a lot.
Yeah, thank you, Aurelia.
Yeah.
Thank you.
Yeah. So our last speaker now. Prashant, are you here?
Yeah, I'm here. Yes.
Okay, good. So our last speaker for the day is L.A. Prashant, who's a faculty member at IIT Madras, closer home for me. So he did his PhD at ISC Bangalore, then spent a year at Maryland. 2 years, did a postdoc there, and he's been here now for quite some time. So he works primarily in reinforcement learning, seems to be a real expert in it. He's offered this course a number of times, I see from his homepage. Yeah, Prashant. Yeah, you're on.
Okay, I'm trying to.
I think now you're co-host, I think. No. Oh, well, I mean, I'm not co-host.
Just trying.
Acha. Okay. Yeah.
Yeah, sorry, I was trying to share screen on a new device and I have to change some system preferences. Okay, is my screen visible now?
Yeah, it is. Yes. But it's a bit small. Maybe you should just expand it a little. Oh, who is it? Can we do it from this end? I don't know.
I don't see your screen. I see.
You don't see the screen.
Zoom.
I see the screen, but I don't.
I don't see any slides. I see a Zoom slide.
Okay.
Oh, you're right. It's only a Zoom slide. Yeah, sorry. I thought it was.
Okay, just kind of. I was trying to do 2 monitors. I'll just work with one. Should be easier now.
It is that other one also. Yeah, I think is this. Yeah.
Okay. Yeah. Okay, so actually there's a French connection to this work. So I'll start with some trivia. I was a postdoc at INRIA for 2 years, 2013 and 14, and this work actually started there. My collaborator, all 3 of us are at INRIA, but we have drifted. And it took us a while. This paper got published this year simply because all of us have been moving between continents. I think we added each one of us added a family member also. Changed 2 continents, added family members, and finally after like 5 or 6 years, this paper got published. So I'm happy to talk about this work. So it's a long title, but for people familiar with reinforcement learning, temporal difference learning is one of the star algorithms. And of late, there's been a lot of interest in trying to derive non-asymptotic bounds for this algorithm. And this is one such work where I managed to derive some bounds under a simplified assumption, which I will discuss. Okay, so this is like the shortest possible course on reinforcement learning, crash course, a couple of slides. So in reinforcement learning, what we care about is what is called a value function, which is highlighted here. And it's an expectation of a infinite horizon discounted sum of rewards for a particular policy, which says how you choose actions, and S is the starting state. So you keep on accumulating rewards while choosing actions using a certain policy, and the expected total discounted beta is a discount factor between 0 and 1. So expected discounted reward is this V pi, the value function. And now it's very well known that it's a fixed point of a certain operator you can, which is defined here. So And the question now is, okay, so how do I estimate this? So the classic algorithm is, I mean, we are going to deal with the simplest variant of TD, which is called TD0. Here, what you do is you do an incremental update to estimate this value function Vpi that I told using a sample path, which is simulated from the MDP using the policy that you have given. So pi, so for this entire presentation, you can assume pi is fixed. Okay, we are not going to look at any control problems where you're trying to optimize pi. Just fixed pi, you want to evaluate how good or bad that is, and the performance metric is the value function. Now, this is the classic algorithm, and major drawback about this algorithm is that you need to store a lookup table, an array in simpler terms for each state, and that can become computationally cumbersome when intractable on huge problems. So one way to work around this is to use some form of approximation. The simplest you can start with is linear function approximation. So in linear function approximation, what you do is you approximate. So this is like the complicated version of linear regression. So you have a function and you approximate it using a linear architecture. You have features which is coming from a different box, which is outside the scope of this talk. The talk here is trying to figure which is the best parameter theta to choose. So, and this approximation, the sanity check is the dimension, the feature dimension, or this feature dimension or the parameter dimension, which is both the D, has to be much smaller than the cardinality of the state space. Otherwise, there's no point. And now, what TD does, the approximate analog of TD with this architecture, it tries to find the fixed point of a, so I already defined T pi earlier. If you manage to remember that, then with approximation, you have to throw in an extra bit of projection, simply because you no longer have the luxury of considering all possible functions. You are restricting yourself to a linear space given by this script P. And within that, you want to find the best approximation. A reasonable thing is, instead of solving V pi equals T pi V pi, you solve this approximate version where this phi theta star is your approximation, your approximate value function. And that is this. Now, this is all classic material. I haven't got to my contribution yet. Next, the point is, how do I find this from a sample path simulated using the policy pi? So you have the function approximation analog, in particular the linear function approximation analog of TD. So this is the algorithm, and this RHS, whatever is highlighted, you can believe me that it's just a fixed point iteration. So if I take the expectation of this and equate it to 0, I would get exactly this phi theta star equals pi T pi phi theta star. So this is one way. So this is a classic stochastic approximation algorithm. You want to find the 0 of some function. So what you do is you take you remove that expectation, take a sample, and do your stochastic approximation using a step size, and that will find the 0 of some function. So here you want to find the fixed point, you can obviously use this. And the question now is, does TD0 converge to theta star? It's not unconditional. Any theorem, we need some assumptions. So I'll briefly discuss the assumptions. So the first thing is, you need the Markov chain to be ergodic. For a simpler setting, we assume it's irreducible, aperiodic, and imagine it's a finite state space setting. So you get positive recurrence also. And so that implies the existence of a stationary distribution. And then the features should make sense. So you have a feature matrix, you take all the features as row, put them as row vectors. And you have a very tall matrix, D columns, and number of rows is the same as number of states. Now this matrix, we want the columns to be linearly independent. It's not good to have redundant features simply because, the approximation, I mean, some of the claims get hurt because then the theta star, which is the limit of TD, will not be unique. The projected fixed point, the theta star will not be unique. So we assume that this tall matrix, feature matrix phi, capital Phi, has full column rank, and which also implies that it has a minimum positive eigenvalue. And for simplicity, it's not integrable, but actually bounded. But you can turn this into an integrability condition under the stationary distribution. For sake of simplicity, I've just said that these features and rewards are all bounded by 1. You can make them integrable with by throwing in a stationary distribution and expectation. And the step size conditions are classic stochastic approximation conditions. And the last thing is, there is a certain notion of mixing time. So this looks like a mumbo jumbo assumption, but this is the, if you look at the TD update, this is the minimum possible thing you would need. The difference, why do we get this thing is that, you have a stationary distribution psi, and the samples come, you have a Markov chain underlying every policy. So you don't start sampling from the stationary distribution, start with some initial distribution, and you keep on applying the transition probability matrix. So that should converge fast enough to the stationary distribution. So these expectations, the difference should not be too large. So this is some integrability condition that ensures convergence. And I mean, this is easily implied by simpler problems, where, you have geometric ergodicity, like finite state space problems with their, irreducible chains. So it's easily implied, but this is a more general assumption. This is like the minimum possible that you would need. This would not be the focus of my work. I'm not working on mixing things up, but I'm more working on trying to derive a non-asymptotic bound for TD. So what is the limit of TD? Limit of TD, now the point is, if all of this passage is not clear, maybe if you're not familiar with reinforcement learning, you can still get something from this talk, as long as you just remember that you want to solve, what you're trying to solve is a linear system, however complicated the individual components A and B are. You're just trying to solve A theta star equals P. This A matrix has a tall feature matrix, has a diagonal matrix with stationary distribution entries along the diagonal, and P is the transition probability matrix of the Markov chain. And so this is this. So and B is whatever. R is a vector of single stage rewards. Now you want to solve A theta star equals B, but the point is you cannot solve it explicitly. All you get is a sample path, and from that you want to get to theta star. So that's the thing. So the point is you don't know the transition probability matrix P, you don't know the stationary distribution underlying the Markov chain. You know that they exist, but you don't know them in a closed form or explicitly. So you sample and try to get to this theta star, and you want to be as efficient as possible. And so we know actually, so this is a classic result, Implicit Van Roy, where they showed that, the TD iterate that the algorithm, the stochastic approximation algorithm that I presented, TD0, converges to theta star almost surely as n goes to infinity. It's in particular the solution to this system of equations. And now we care about non-asymptotics. So the question now we want to address in this talk is what happens in the short run of TD0. How good or bad the convergence is. Is it converging fast? Is it converging slow? How do I set the step sizes? All of these come into consideration. So this is the summary of the bounds. So recall, so this whatever is there is the update, TD0 update, and we know that theta n converges to theta star. You can believe me or read Van Roy's paper. At this point, you either know this or you have to believe me. Yeah. Now, what do I want? I want to bound the rate of convergence for all m. So what I want is I want a non-asymptotic bound which bounds this error, okay, theta n minus theta star, either in expectation or I can get a high confidence guarantee. Okay, and the question now is why 1 by square root n? Because it's an algorithm which is handling noise, which is much more complicated than a martingale difference. You have Markov, have mixing and all things, but with noise, with sampling, 1 by root n is the best possible. You can make this all trivial and turn this problem into a mean estimation thing with noisy samples. I don't think you can get better than 1 by square root n. So 1 by square root n is what we hope for. And we want to establish bounds like this, both in expectation and in high probability. That's our goal. And what are the things to be chosen? The important point, anyone who has done stochastic approximation implementation in practice, the most famous example is stochastic gradient descent, would have suffered with this learning rate or step size parameter. How do I choose this? So at least in theory, we'll try to figure how to choose this so that I get a order 1 by square root n bound. So that's the goal. And sometimes for non-asymptotic analysis, we also look at projections so that the iterate is stable. For the asymptotic convergence, we don't need this, but to make the analysis go through, in some cases, we would have to project. Okay. And the setting that I'm going to look at is going to get rid of this mixing issue altogether. This is the first thing that you can do. Imagine, hypothetically, imagine the samples, when I do the TD update, imagine the samples are coming from the stationary distribution, which is like saying that I pick a state, say at time t, I pick a state st from the stationary distribution, and I pick the next state from the transition probability matrix using this distribution given by the transition probability matrix. And then I take this and then get the reward, and I feed this into the algorithm. I feed the sample transition to the algorithm. It's important to note that I'm starting in the stationary distribution, whereas the actual TD0 algorithm, you can start with any distribution. There'll be a mixing phase, and then the stationary distribution kick in. After that, it will start seeing from the samples from the stationary distribution. But for now, at least even in this case, assuming stationary sampling, whatever we call a sampling with IID noise, not a Markovian noise, the analysis is still challenging. And so in this case, the bounds that have managed to derive are like this. Imagine you choose a step size like this. The classic diminishing step size, C by K, we chose C by C plus K, which is a minor variation to that, but it's like C by N. And the important thing is we already have assumed that, this matrix A, okay, so one more thing to notice is if you compare with normal least squares regression, this matrix A is not symmetric. You can go back and look up the definition. It's not symmetric. It has a I minus beta P term, which is multiplying inside. So it makes it non-symmetric. So, but its symmetric part, we are assuming it has a minimum positive eigenvalue. This is usually implied by assuming there is a stationary distribution and the feature matrix has full column rank. Those two assumptions will usually imply this. Now, given this assumption, now if I set the step size as inversely proportional to this minimum eigenvalue, then I'll get a bound like this, the bounds that I wanted to derive. I'll get both of these bounds with certain constants. That's the first message. Okay, I hope everyone is clear. So this is the first thing, but what is the problem with this bound? The problem with this bound is, you need to know mu. If you want to get 1 by square root n rate, then you need to know mu. Otherwise, you won't get this. So the step size, only if I set it inversely proportional to the minimum eigenvalue mu, then I'll get this. Okay, that's actually a little problematic, and we'll try to get around this assumption. But this is the first thing that we have derived, and the way to get around this assumption is like it's give and take. You get rid of the assumption that you know mu, but then the rate will be slightly weaker, very, very slightly weaker. So the idea is this. If you look at the previous case, I took a step size which was C by C plus N with alpha equals 1. Now here I'm going to take bigger steps. Alpha is something which is between half and 1, but 1 is not included. And what I'm going to do is I'm not going to give the bound for the last iterate. Actually, I'm sorry. So this has to be theta n plus 1 bar. So these bounds for the iterate average case are for theta n plus 1 bar. I think I fixed it in a follow-up slide, but this is just a unfortunate typo. So the bounds are for theta n plus 1 bar, which is the average iterate. So I take bigger step size. I take bigger steps. If you look at it, I have an increment. I'm multiplying it by a step size each time, and I'm trying to get closer to a limit, which is theta star. So I take bigger steps, and the bound in the end is not for the last iterate, but for the average iterate. This is a well-known scheme. which was found, proposed independently by Pollack and Rupert 6 years apart, 1988 and 94, I think. Yeah, so it's attributed to both. And now this scheme, this iterate averaging so the point is now this C is a free parameter. The constants would depend on C, but the point is I no longer have the problematic dependence on mu. But there is some give and take in the sense I got rid of a problematic assumption, but the rate I get is not square root n, but it can be made arbitrarily close to 1 by square root n by choosing alpha very close to 1. I cannot strictly choose alpha equals 1 because my constants will blow up. So the constants will blow up. Alpha has to be strictly less than 1, but can be made arbitrarily close to 1. So this is the rate you can get. So there is some loss in the rate, 1 by n power 1 minus alpha by 2 loss in the rate compared to the previous one. But at least you don't have to know something. So you're trying to solve A theta star equals B, assuming the minimum eigenvalue is obviously problematic. If you know the minimum eigenvalue, you know a lot about this system, A theta star equals B. And why even solve incrementally? If you have managed to know mu, you have already know how to solve this directly. So iterate averaging is the practical variation, but the analysis you can do for both. Yeah. You'll have to do, the first step is assuming the knowledge of mu and then try to get rid of it here. Okay, so summary of what has happened in the recent past, say in 2018, in a paper by Dalal et al., they gave bounds for the last iterate, and the bounds are comparable to whatever we have with iterate averaging, 1 by n per alpha, where alpha is strictly less than 1. And then Bhandari et al. Gave last iterate bound, but assuming knowledge of mu, they get 1 by square root n, otherwise they get something weaker. There's another work where they do averaging, but they don't use diminishing step size, the third row. They use constant step size. And then what I have not written is this constant, a step size constant would depend on some underlying, eigenvalues of the matrix A. So you would still, you get 1 by square root n, but there is a caveat. There is actually a caveat. And in our work, we give bound for last iterate without averaging. We need knowledge of mu. Otherwise, we don't need knowledge of mu, but the rate is somewhat weaker. But it can be made very close to 1 by square root n. That's really the high level summary. This kind of logic works even for, classic gradient descent, or if you go back to any stochastic approximation schemes. But the problem in a RL setting is knowledge of mu is not known. You're trying to solve the system purely by sampling. You don't know many of the underlying quantities. You don't have the direct information or any prior information about these matrices. All you have is you get samples, and you can come up with a iterative algorithm, stochastic iterative algorithm or stochastic approximation algorithm, which will converge there using these samples. So in RL, assuming knowledge of mu is problematic, so this is the best you can do. Now, maybe some of you may have a question saying why, if TD0 cannot see, samples from, stationary distribution directly, is there, okay, the probability bounds also comparisons are similar. I'll skip this. But is there any, apart from a theoretical investigation, is there any utility to this exercise? Of course, I got a paper. It helps my career. But is there any utility to this analysis, like assuming stationary distribution, I start sampling from stationary distribution? Is it really useful? So that was, so yes, there is. And I'll show you a reinforcement learning setting where exactly all this analysis, you can do copycat arguments and get bounds like with inferences like whatever I gave. But it makes perfect practical sense. So that's the least squares temporal difference learning algorithm. So I'll get going with that. So the point is, instead of doing online TD, which is like, you take a sample transition, you do an update. You take another sample transition, you do an update, and eventually get to a point theta star. Instead of that, imagine you collect a bunch of sample transitions and you solve your system using that sample transitions. Okay, so that is a batch algorithm. That is like the batch cousin of TD. So it's least squares TD, least squares temporal difference learning. And it's a batch algorithm. So what you do is imagine you collect a bunch of sample transitions. I was in state SI, I took some action, I saw this reward, and I saw next state. I collect a batch of size T. And then I approximate the theta star by using just this batch. So this is my solution. Again, the lack of symmetry in this matrix can be seen from this. If you look at this term, this multiplies here. So this matrix AT bar is not symmetric. So this is a complicated cousin of whatever you would see in a least squares regression problem. And now imagine I want to solve this. So let's just zero in on this problem. You want to solve a linear system. And if I want to solve this incrementally, say I have T samples, so I can do incremental inversion. And each time I add a sample, it's order of D square complexity. And then I have T such sample transitions, so order of D square T. Now the question now is, can I bring this down, complexity down to order of dt, which is like in each iteration, instead of solving this inverse using the classic Sherman-Morrison lemma, incrementally finding the inverse. Instead of this, can I do something to reduce this, dependence and save some computation, but not lose much in terms of convergence rate? So that's the question we want to answer. And the answer is yes. Okay, so this is important because even though we are doing function approximation, the features could still be high dimensional. There was actually, when I was doing this, there was a computer Go example. Now we have AlphaGo, but before that had this with 10 power 6 dimension for features. So solving, inverting this matrix is computationally prohibitive. So one way to work around that is I'll do TD on this batch. I'll do an incremental algorithm, which is very much like TD0, but I'll only iterate through the batch. I'll take samples from this batch alone. Can't go outside the batch. T sample transition, I take samples from this batch. And that way I'll reduce the complexity to the order of dt. And now the theory that we'll do, experiments I won't be able to discuss today, but theory will show that this batch TD is almost as good as inverting the matrix directly and solving that linear system. Okay, so how do I do this? I have T samples. This is like the friend of SGD. You take one of the sample transition and do your update, and your update is like this. So what is the connection to stationary distribution? If you, instead of this, if I pick samples from the stationary distribution, instead of picking random sample from the batch, if I pick transition samples, sample transitions from using the stationary distribution or the IID sampling, then this becomes the classic TD0 algorithm. So the difference is in classic TD0 algorithm, you can pick from the entire, you have the entire Markov chain at your disposal. Whereas here, you just are limiting to just a bunch of sample transitions in a batch data set. And in terms of analysis, analysis is the same. But the point is, this is a practical algorithm because I save the complexity. If you do this update from right to left, this is an order of D update. And if I do T steps of this and look at theta T, then that is very close to the LSTD solution. So that's what we will show. The limit of this is not theta star because you're just restricting to T samples, but it's actually theta T hat, which is the LSTD solution. And I save computation, and this is practically viable. So there is an angle to this finite time analysis where all the analysis that I did is applicable to this, as well as the stationary sampling for the vanilla TD0 algorithm. But stationary sampling does not make practical sense, but this makes practical sense. I can collect samples and instead of doing LSTD on problems where the feature dimension is large or huge, whichever adjective you want to use, but you can do online, you can do batch TD. So you just run TD on this batch. It's like TD algorithm, except that the sample transitions are picked uniformly at random. And the bounds that, assuming assumptions similar to whatever I listed before, features bounded, rewards bounded, and lambda min having minimum eigenvalue, which are like the batch counterparts of the assumptions that I had before. Features bounded for all states, here features bounded only for the states that I look at, and things like that. So everything all the assumptions restricted to the batch data set. And under this assumptions, what we have is bounds like the whatever I presented before. Take a step size which is inversely proportional to mu, And then I get this rate, 1 by square root n rate. And I can do averaging and get rid. I mean, this is a very boring slide with all the constants. But if later somebody asks questions, I thought I kept this slide so that I can pinpoint to the exact nature of this bound in terms of constants. And this is the problematic thing which I already hinted at. You don't know mu. So one way to get around this is do iterate averaging. And iterate averaging is exactly as before. So you do theta n bar and bounds are for theta n bar. Thankfully, I don't have the typo here. So I take the average and this average converges at the rate 1 by n power alpha by 2, where alpha is strictly between half and 1. But the step size constant or parameter is free. The constants would depend on C, but at least I don't have to know the knowledge of mu to get a order 1 by a bound which is almost like 1 by square root n. I can't choose alpha equals 1 for reasons I have illustrated before. So this is the most boring slides. Maybe there's one more boring slide after this. These are the constants. Yeah, that's where the boring slides end. And this is a bound that I think someone in RL. So the point is this. So I used an approximation to LSTD. So if I had done LSTD, I would have got some convergence rate. Now I didn't do LSTD. I did an approximate version by running TD on the batch. So does that hurt the rate of convergence of LSTD to the optimum, no true value function? And that the answer is no. The answer is simply no, because if I had done LSTD, I would have got the first two terms. And because of the approximation, this is the computational error. The first two terms are there from the LSTD analysis. They're exactly the same. Now, because of this approximation, I added a term which is of the same order as the other term, the second term. So if I run TD on this batch and do T iterations of TD, then the order of this error is the same. So I added something, but the overall order I did not hurt. So because of this approximation, I'm converging to the overall value function at the same rate as LSTD, modulo some additional terms, but they're not hurting the rate. So the message is clear. You can save computation and also you don't hurt the rate. I mean, barring some constant, but you don't hurt the rate in terms of the dependence on the batch size. So that's where I will end. I'm open for questions now. Yeah. Okay, for those who don't want to ask a question, I think this comic.
No. Thanks. Good, nice.
Thank you. Well, do we have any questions from the audience? Okay. Well, no. Okay. Well, thank you very much for this talk, and I want to thank all the speakers. It was really very inspiring, a lot of great research presented. I think since we're late here, and I think everybody is getting a little tired, we will forgo what the program might have suggested, a discussion session. We'll have a roundup discussion tomorrow after the explainability and robustness workshop.
Yeah.
By the way, I'm Prashant. I think the Zoom display name was broken, but yeah.
It's okay.
That's my daughter because she took an online class.
Yeah. So please join us for tomorrow for the discussions, because that will be nice if possible. All of you, all the speakers.
There is no discussion now. The discussion happens tomorrow.
Yeah. We're late.
And quite late.
And come hear the talks too, if you can, because I think they'll be very good too.
Sure.
Yes. Yeah. Thank you, everyone.
Okay,
all right, thank you. Have a good end of your afternoon. Bye-bye. See you tomorrow.
Yeah. Okay. See you. Bye.